I think it's a very important, OARC is a membership organization. I feel it's a very important part of running a membership organization that we are transparent and communicate to you, the members, and the wider community what it is that we're doing. The way we try and do this is not to eat into huge quantities of workshop time by taking forever to drone on. Rather, you will find a bunch of written reports. There's a quarterly report from me, and there's also several engineering reports. And really, the presentations that we're doing over the next hour are a quick overview of what's in the reports. If you read the reports, happy to answer any questions about the content. If you see anything that's of interest in the slide deck and you haven't read the reports, you can find more detail in the reports. So, OARC's mission statement, what are we here to do? We're here to make the DNS work better, and to do that in a way which builds relations amongst our community, encourages interaction between the operator and research communities, and transfers knowledge. And one of the main ways that we do that is through these workshops, but it's by no means the only way that we do that. Our membership has been pretty steady. I really appreciate the solid support that the members have given us over the past 2 years, which have been very challenging in many ways. Many of you have upped your commitment, and it's been really good to see that ongoing support. And we have a very diverse member community, as you can see from all the names that you may recognize in our member tree. We haven't done an update since OARC 36 in the fall of 2021. This isn't just everything that happened since the last workshop, but since the last 2 workshops. 2021 was a pretty good year. During the pandemic, we focused on bringing in as much grant funding as possible, and we had a bit of a success disaster there. There was some good work done, and I'm pleased to say that all the work objectives that we made were delivered on time and successfully. All that work is completed, and we don't have any outstanding externally funded work at the moment, although we did just submit another grant proposal. 2021 we did 3.5 online workshops, 3 2-day ones and a short one. As I say, thanks to all the member support, we exceeded $1 million in revenue for the first time, which was a great milestone. And that's allowed us to build up pretty much the best part of a year in operating reserves, which is a very good position for any non-profit to be in. Other things that we achieved as 2020 went on was significant progress on systems cleanup and automation. What have we achieved this year so far? We've appointed a new systems engineer. Mike Baer has joined us a couple of months ago, so that will significantly help with the huge amount of backlog and systems work that we need to do, and he and Matt are already making progress on that. Privacy Committee, I'd like to thank Benno and Sarah Dickinson in particular for moving that forward. They've done our report. Benno will be saying more about that in a minute, but there's a report on the existing data usage. There's a draft charter which the board should be able to sign off very shortly, and we've seen some very useful expert input from PIR and a number of other parties. We came up with a new software development strategy, which rather than trying to support everything all of the time, will focus on particular areas. For now, that is focus on testing tools, and Derry's focus on that has allowed us to generate some interesting new features for Check My DNS, including updated user interfaces and DNS-over-QUIC support. And once again, we did our annual Day in the Life of the Internet data collection that happened for 2022, and we released the raw data for that almost immediately, and the data set has been processed. Other achievements this year, we did our first hybrid workshop in Austin. As I say, that was mostly remotely attended, but it was a good test bed. And also to get back with co-locating with another event at NANOG. And here we are in Philadelphia. We had hoped to do the workshop maybe in May, June, but we decided the various challenges meant that it was easier to co-locate with ITF, and it's the first time we've co-located with ITF in about quite a long time. It also meant the team over the first half of this year were able to get out and meet with people, meet with the community, represent OARC at a bunch of industry events, and I think we've certainly found that very helpful and motivating, and I hope you found that useful as well. It's also led us to some internal planning meetings, which is kind of boring stuff from your point of view, but it meant that we were able to get the whole team together, including our 2 pandemic hires, first face-to-face for the first time. We did our first Fremont site visit in over a year, and done quite a bit of engineering planning. We also just did an all-hands this week as well. Matt relocated our site in Ottawa, which is generously donated by Sile, and we've purchased some new routers which will get deployed over the next few weeks and address some long-standing issues with these. And Mike has been gradually spring cleaning all our websites and getting the platforms for these up to date. I'm pleased to say that 5 of our 6 board members are here, so if you'll please do speak to them. They contribute a lot to OARC, both in terms of wisdom and time. They're all here. Program committee, again, program committee has been doing a great job since they were appointed at the start of the year with quite a few new members. Again, they are all here in person, with the exception of Hazel, who is our remote participant and helping out there, and also Willem sends his apologies. So again, a big thank you to the program committee for all the work that they do. They're certainly helping out in all kinds of ways this time, and put together what I think is a great program. This is the team. We don't all work full-time for OARC. Most of us spend most of our time on OARC, but do other stuff as well. As I say, Mike has joined us from Berkeley, California. This is probably the first time that most of you have met our new membership coordinator, Steve, who joined us a year ago. And again, Steve is at the registration desk. He's keen to speak to you, so please speak to him. As far as our workshops are concerned, we're continuing with hybrid like the rest of the world until further notice. The last 2 years, the AGM, the formal member business and elections have been standalone. That seems to have worked quite well, so we will be sticking to doing that in an online format this year, which also frees up more time for program and content at the autumn workshop. Our planning at the moment, that's going to be in Belgrade, Serbia, co-located with RIPE 85 and with Centrotech. We still need to work out the formal details of that, so you should regard that as provisional until we announce registration. But with this, we have 2 members in Serbia. They're keen to work with us, so you should assume that that is a plan. And then we have a firm commitment for OARC 40 to co-locate with the annual meeting next February in Atlanta. 41, we're reviewing at the moment. Running 3 workshops was our plan before the start of the pandemic. It's proving a little bit of an operational stretch. So we're reviewing at the moment whether we go for 2 workshops a year or 3, or maybe we do 2 and 1 virtual or 1 short one. Also ties in with whether we get back to co-locating with ICANN IDS or not. Your feedback on that is welcome, but watch this space as far as spring next year is concerned. And it's great that we get sponsor and patronage support for our workshops, and if that's something you're interested in doing, then please speak to Dinesh. So what we got planned for the rest of this year and into next year, we did some engineering objective setting in Fremont, so we have some quite ambitious plans there. Many of you will probably be rolling your eyeballs when we say, yes, we're really going to get the new data store project finished this time, but now that we've got Mike on board, he's able to focus on that and free up Matt for doing other things, so they'll be saying a little bit more about their plans for that. The intended output of the Privacy Committee is restructuring the data participation agreement to make it more privacy-centric and cloud flexible for the future, so expect some progress on that. We've been discussing this week about ways in which we can make the integration of the member portal. Steve will be saying a bit more about the portal shortly. The Mattermost chat and the workshop registration, a slightly less convoluted process for you all, and also a more efficient process for us. It has been nearly 4 years since we last increased our fees. We're already seeing various expenses increase at the moment. So we're planning to increase the OARC membership subscription on the 1st of January next year. Exactly how much we're going to increase it by, we're going to be keeping a careful eye on the inflation figures this year, but there will be a proposal for member approval at the AGM for that. I'm also at the moment trying to hire an office administrator so that we can make more efficient use of the technical and other parts of the team, and also my time, and that's also intended to facilitate the transition to new leadership when I eventually step back from executive role in this industry, which is again something that we will hopefully make progress with before the end of the year. One other thing that remains to be done is that, no, wait a minute, that's not quite yet. That is my update. I will now hand you over. So Benno is our board chair, and he's going to give you an update on the progress of the privacy committee.
Thank you. Well, welcome, Benno Overeinder. Next slide. I'm in control. Yeah, I'm in control. So first present here the OARC privacy committee members. We have Joao, Sarah, Dave, George, myself, Sidan, and Steve in the privacy committee, subcommittee. Joao is in the room over there. Tail is over there. Thank you. And Steve over there. So please contact us later if any questions. We're also very happy that we have an external consultant. This is Beth Bacon from PIR. I will come to that back later, how she advises, and is well a great support to our committee. So in, I think, OARC 36, autumn last year, we presented our subcommittee working on the privacy, and our goals, etc. So this is an update where we are now, right now. So made some progress. So this is kind of the major goals we set out in our charter. And it's, first of all, we have to identify if the current participation agreement and data sharing agreement are in compliance with data privacy or privacy laws in different regions. Another goal, one of the important other goals of the privacy committee, is to increase or to maximize the usability and the usage of the data OARC is collecting. And you see some other goals that are a little bit lower below the list, or lower in priority, or less visible. But the other thing is important. The end is, of course, we give advice to the board on changes on the data sharing agreement and the participation agreement. And part of it is also propose a process to appoint a privacy officer. And that's not a person, it's a role any person in the organization and staff can fulfill. Good. So from the charter and the milestones, we finished some of them. We drafted charter, we sent it to the board for review, we got feedback, we have to incorporate the feedback, and we'll publish the charter on the membership mailing list. Maybe also DNS operations, but it's more technical, so primarily the membership mailing list is our the mailing list we communicate. We did conduct a survey. We presented the first results at OARC 36. Then we reopened the survey, we got additional data points. We wrote a report, presented to the OARC board for information and for feedback. So one of the last bullet points, so we did some analysis on publications. Actually, that's in italic. We still have to do some work on that. Next milestones of the privacy subcommittee is, well, do the kind of the real work here and identify the deficiencies with the current agreements we have regarding and in relation with the privacy laws. So we really get great help from Beth Bacon. She managed the process at PIR. So she's not a lawyer, she's stressing that. But she managed the process. And with her experience, we go through the same process here at OARC. It's a smaller organization, but we have to go through the similar steps. And also we have looked at the different privacy laws in the different regions, and advice is take the most strict privacy law, the GDPR, as an example, and you're good for 80% over the world. So that's what we're heading for. So you also strongly advise involve a lawyer, a consultant, that helps us through the process. Because from a lawyer we have to get the suggestions to fix all the deficiencies in our agreements. Good. Of course, we will come back to the community with a survey or another presentation for feedback from the community. And eventually we'll make a number of recommendations to the board for changes in the different agreements. Good. And also important to maximize the usage of data and usability. We also make a number of advices or recommendations to the board about the infra strategy and making the data available. Good. Then a call out to you, to the community. If you have any questions, please reach out to us. We are here in the room for today and tomorrow. Steve is our secretary, so Steve is always a good contact point. If we're not here, send him an email. And he will make sure that it's on our agenda. If you have an interest in this topic, questions, suggestions, anything, please reach out to us. We're open for feedback, or actually asking for feedback and your expertise and input. And if you might have a legal advisor in your organization, a lawyer, well, please reach out to us, because we're not the lawyers, we're not the legal advisors. So we can help. We can use any help here, and also, well, with qualified people that have experience in this area. That's it. Any questions? No? No questions online? Okay. Thank you all.
Okay, thank you, Benno. So, next presentation is from Steve Sullivan, our membership coordinator. Steve is going to be telling you a bit about how to make use of the OARC portal and what we've been doing with it to make it easier to use. So, Steve.
Thanks, Keith. Hey, everybody. Thank you for coming. My name is Steve Sullivan. As Keith mentioned, I'm membership coordinator for OARC. My role in the organization is mainly to field new membership inquiries. Oops, excuse me. Let me put this down here. Field new membership inquiries. If anybody has any friends or leads they want to send my way, I'm happy to speak with them and give them a little information on what the organization is about and what we do. I also like to assist current members in navigating the OARC landscape. If you're lost and need a point in the right direction, please don't hesitate to give me an email or a call. I will take phone calls, or Mattermost, and you should all have my Mattermost handle. And just general questions about membership at OARC. Today I'm going to give you an update on the OARC portal, what we've been doing since the AGM back in November 2021. Jerry's put some work into it to make it a lot more useful and try to evolve it from what was an older, less useful portal. And you all actually have access, if you're a member of the organization or a participant of the organization, to set up your profile. And it's important to keep that profile up to date. Make sure you're on top of changing it when employees leave, or if somebody is promoted to another department in your organization. Please take a stop in the portal and do make that change for us, because that actually drives the membership or the member-to-member contact database. And that actually, if that is not up to date to the minute, it can cause a little frustration for folks when they're trying to reach out during periods of time where there's an issue resolution, community response to an issue that's going on out there in DNS. So please do keep that up to date. I'm always there to help out, so if you're too busy, just throw the information my way. I'm happy to do the work for you. What's the next slide here? So the upgrades we've done since November of 2021, they're put into 3 different categories. First, since this is an iteration from a previous version of the portal, we had to do a lot of cleanup. So we revised some fields and layout. Actually, Jerry did that with some of my counsel input. We removed a lot of unneeded fields that were artifacts of the old portal. They didn't make sense, and I'm sure it caused some confusion for people when they stopped in to look at it. So hopefully, if you look at the portal in its current state, it makes a lot more sense and is more informational, a lot more readable too. We renamed a lot of fields so that they are clear in what they actually are. Prior to this last iteration, some things just didn't make sense. So right now, when you look at something, it says exactly what it does. This is your start date for your agreement. This is your end date. So you have those milestones. You know when your renewals are coming up. And I always do reach out to remind folks when renewals are coming up. But if you do have a question in the meantime, please stop in at the portal. We also added a vendor portal field. That is the new procure to pay movement is starting to take hold. So we see a lot more folks using a third-party organization to manage that, which is our interface for sending invoices and paying. And if you could make sure that's up to date, companies are sometimes changing them year to year, and we just can't keep up, and that causes a little bit of slowdown in the renewal process. So please take a look at the portal and do enter your vendor portal information if you indeed know who that is. We've enhanced member info management. By that I mean the membership term info is more clearly displayed, as I just mentioned. We've added contact POC tags, so if you want to triage who your contact people are, your org manager can go in and make somebody a point of contact. I believe you can make yourself a point of contact even if you're not an organization manager. So it's just another way to improve the communications between members of the organization. We also added the editable names field. This is mainly for the org managers or our first point of contact, the person that manages the data in the portal. This has come about because of the era of mergers and acquisitions. We're seeing a lot more companies either come together and have two names, or maybe it'll be a conglomerate with 5 or 6 names, and that actually helps to improve the search. For instance, we recently had an issue where Slack had some problems, and we realized that, oh, Salesforce is here. They acquired Slack. We didn't have the Slack folks in. We were able to get them on the portal within minutes, answer the issues, and watch this get fixed in real time on Mattermost. It was very cool to see, and it's nice to see that we actually are helping to make a better internet that way. We also updated help text throughout. There were actually old artifacts from the other portal or the older portal that were still in there. They persisted and it just didn't make sense. So we're trying to make it clearer and shorter. That's what I mean by readability. If it's long, people aren't going to spend the time to read it. So we tried to make it as useful as possible in that respect. Also, I shortened the portal welcome letter. I have a tendency to be a little long-winded, as you probably will find out now. It was too long, so we want to shorten it down to where that email, when it goes out in the onboarding process, is just simple, easy to read, and you know exactly what you're looking at. We don't want to information you to death. It's just simple. And again, if you have any questions, if that email didn't come through, please give me a call. If when you add a user and they don't see it, just shoot an email, shoot a text, however you want to get in touch with me, I'll be able to help out. And the last is automated email reminders. This is important in that we may not see a notification that a member contact is not in the portal. And that could be a liability in the fact that we're still sending them members at emails. There could be some private membership only information that's going to that person. Now it may go to a dead email address, but if they're using a personal email address in the portal, they may still be getting that when they're not with your organization. So keep on top of that. It could take us a couple weeks to catch up to that, and once we do start seeing the bounces come in, we do try to do that, send out an email to the organization manager or look into LinkedIn. It takes me a little bit to figure that out, but I don't want to go in and disable anybody without member input or participant input. So if I do reach out on that, I'm not trying to bother. I'm just trying to help you guys out in cleaning that up. And the emails are also designed to do that, and they go out quarterly. You do have the freedom to do it on your own, so if you see the email, you go and review those your contact list. Say your phone number changed, just go ahead and change it in there. If your email changes, please feel free to stop in. If you're not sure how to do it, give me a shout, please. Also, for supporters, we have instituted an in-kind submission reminder. The supporters have a in-kind contribution that is required of their agreement in order to participate at their level, and we realize that everyone's very busy, and that reminder is just designed to be sent out to say, hey, you've got this coming up. Please submit that information to us as soon as you can. We need that. We do need that before the end of the agreement preferably, and we do need the in-kinds to be submitted in email so we have a chance to review them. And it's not ideal to do it at the time of renewal. That just slows the whole process down. Let's see. So some takeaways and portal benefits. I want to stress the benefits of this now is the old portal was not a self-service portal. This portal, Portal 2 that Jerry has put together, is a self-service portal. You have access to it, so you can drive that destiny. You can make those changes. But I got your back. Again, you feel free to come out and talk to me if you want me to make those changes for you. We consider this the authoritative member information source. It's the cornerstone of your membership, and it's going to get even more important as we move forward because we need enablement tools like this in order to do things quickly and easily to support our membership. We have things in the back burner, such as maybe putting agreement copies in there, maybe delivering the discount codes for the workshops that way. So it's a one-stop shop to get everything, and as we iterate, we really want member input. That's very helpful. I'm running out of ideas, and it'd be helpful to hear from you all what you would like to see in there and where you would like to go. We've gotten some info or some input from Paul Ebersman. Thank you, Paul, for that. And we see that there's like a direction we can go in, but again, more member input would be helpful. This is a member-controlled contact database, but again, it does require the active care and feeding to keep it current. So again, so remember that liability. It's self-service for me. I got your back. Let's get here. Oh, if you do need help, reach out. Again, as I said, Jerry and I are happy to do one-on-one demos of the portal if you want to just a refresher, if you're not familiar with what it looks like now, or if you just want to understand how better to use the portal, please grab me, and I'm happy to sit down with you for a few minutes during the breaks and just go over it very quickly. It won't take very much time. It is pretty simple. The design of it, it's elegant, it's very basic, it's not overdone. So please reach out to me if you want to be able to take a look at the portal in greater detail. Any questions? Okay. Thank you very much.
Okay, thank you, Steve. We're still running about 15 minutes late, so just in case anyone joined and wondered what's going on with that. Next speaker is Jerry Lundström. I'm sure most of you know Jerry. Jerry is going to be talking about what he's been working on and what his plans are on the software engineering side of the organization.
Good morning, everyone. So, my name is Jerry Lundström, and I'm the software engineer at OARC. I maintain and develop all of our open source tools and some of our services. And we usually give out a report on the last couple of months since the last meeting, but this time I wanted to do something different, and I wrote a blog post instead to try and make it a bit funnier to read, hopefully. So I linked to all my other blog posts about the things I've been doing since it's been 9 months since the last meeting. And I wrote a story about a survey I posted earlier this year and the process of getting to the result of that and the decision. So the TLDR on that, as Keith mentioned, is that my focus going forward is going to be on Check My DNS. And to iterate what it is, it's a tool to test the end resolver to the authority. So I do some things in browser and generate queries, and I control the authority, and in that way I can test the authority in different ways. And I got inspired during RIPE 84 with the talk Sarah Dickinson had about DNS-over-QUIC. Quickly looked at support for that, and in a couple of weeks I had that running. But I haven't found any resolver software that can talk that yet, so we'll probably get to that in the future. Yeah, and I have a lot of other stuff coming, like new UIs. I want to do one for mobile, one for desktop console with a lot of things, but yeah, UI often take a lot of time to make. So In the last 9 months, there's been 26 releases of our software, over 200 pull requests, and you can see in the word art there which of those softwares has gotten the most updates. And here is also like, yeah, you can see my workload over the year, or the last 9 months, and you can also spot where I have holidays or go to other conferences. And that's basically it, and I'm gonna skip questions, so just come find me afterwards if you have anything. And if you have any questions around our software or our services, feel free to contact me in any way. I also did DEC Grafana crash course stuff. If there's people still interested in that, we can set that up. Or if you have any other issues, you want to have longer discussions, you want to show me, give me access to the system, anything, I'm here for you. So that's it. Thank you.
Okay, thank you, Jerry. So next up, once he disentangles himself from the webcast stuff, I think we need to give Matt a moment, is Matt Pounsett, our systems engineer, actually half of our systems engineering team now, and Matt's going to be giving you an update on what he and Mike have been working on and have planned on our systems infrastructure.
Thanks, Keith. Yeah, so I'm Matt Pounsett. As Keith mentioned, half of our systems engineering team right now. As usual, we've got a written report that we put together that covers this stuff in more detail and a few other things that are sort of lower priority that we haven't bothered to mention in our talk today. So I guess the headline here, which is buried a little bit in the slides, is we brought Mike Baer on a few months ago to help out with systems engineering stuff. One of the things that's been sort of a major problem with systems engineering for the last few years now is we've had a lot more to do than we have time for. So Mike's getting up to speed and has already started taking on some of the maintenance and update tasks and things like that. And as he gets more familiar with stuff, we will continue to hand more work to him. So we're still working on our backlog of issues, but there's an end in sight now to some of that stuff. As well, with lifting of a lot of the travel restrictions and stuff, we've been able to start making physical visits to our sites again, so we're no longer relying on remote hands quite so much, which has made it easier to do sort of a lot of physical maintenance stuff that's been either subpar or not done at all for the last couple of years. So one of those things is we ended up relocating our Ottawa site. So we've had, for a long time now, we've had this sort of satellite site in Ottawa, Canada, which was initially just some basic admin services, a backup DNS server, that kind of stuff. A while back, we moved a copy of all of our analysis data there so that there would be something outside the US jurisdiction for anyone who wanted that for doing analysis work. And all of that has been generously hosted by Sile, providing us with rack space and power and network for a few years now. So they notified us early this spring that they were going to be relocating that site, so we had to do a physical move. That meant we had to deal with a bunch of issues there as well, or rather there was an opportunity to deal with a bunch of issues there. So in the process of the move, we got our own transit, so we're no longer just piggybacking off of Sile. We're using now separate address space. We've done a lot of cleanup of the private address space we were using there. We got a second storage server, so we now have a local to Ottawa backup of the data that's there. We've got some other improvements coming along the way. So Part of that is new routers. So as DNS-Viz users have probably been aware of, we've had issues with V6 in Fremont for a long time now. There's a bug in the OS on our router there that results in random routes not getting installed. So we've got a new router that is now on site. We had a bit of a shipping logistics problem that resulted in optics that we need arriving after our last on-site visit. So we're going back in the next couple of weeks to install optics and stuff so we can actually start configuring that properly. And there's a second router there that's going to be shipped to Ottawa to replace the one that is there, so we'll be able to upgrade it to be able to do BGP and stuff like that. Up till now, it's just been doing static routing. There have been a few updates to applications that we run. Hopefully nobody noticed these, but there's been a few things here that have been sort of hanging on because they were not urgent, not critical, but kind of needed to be done. And now with the extra help, we've managed to handle them. So. Data store stuff, there hasn't really been a lot of change here since the last time we did a report. The sort of legacy NFS systems that we're trying to replace haven't really changed much. There's still a couple of them that are down. We expect that to remain basically until we're ready to migrate data. There's one of them that we can recover, but we're not really going to put the effort into it until we have a place to copy the data to. And the new data cluster, the new Ceph storage cluster, not a lot has happened on that in the last 6 months, but Mike is now taking on that so that I can continue to concentrate on some other things. And hopefully we'll have something to report within the next few months. Yeah, so the hardware for that has been racked and cabled and running for a while. We've recently updated our automated OS installer to deal with the newer version of the operating system we're using, and Mike's trying to get up to speed on the Ceph configuration stuff to get the actual application deployed. So that is sort of the high-profile stuff. As I mentioned, there is a PDF report that goes into more detail that's available in Indico under the agenda. Does anybody have questions about any of this? All right. If anyone does want to ask us anything, I am Matt. Mike is Mike. We can be reached under these names on Mattermost or by email. You can also send general questions to admin if you want to email that way. And yeah, we'll be happy to help out with anything that comes up. Thanks very much.
Okay, thank you, Matt. And also big thanks to Matt for all the round he's done over the past 24 hours and the preceding weeks to get the webcast production going. Just one pleasure that remains to me and to Benno, which is we've always tried to recognize the contribution of our board and program committee chairs. They do a lot of work, and of course, one of the things that's been very difficult to do over the pandemic is to recognize that properly. So we have a bit of a thank you backlog to catch up. There's 4 people in particular that we'd like to recognize. Unfortunately, one of them is here. Joe Abley served on the board for a year, and Andrey Suri served for several years on the board in more than one capacity. And Jan Vlecek was on the PC for a full 3 years and also served as program committee chair. So I'd like to thank them all. The only person that we want to thank who is in fact here is David Lawrence, who served on the board as well. And so a big thank you to David and to all the other former board members and program committee chairs who have helped out OARC over the years.
Thank you, David. Yeah. So we didn't see each other for 2 years. So it's very good that we are here in the same room, in the same place. And also, Dave is not away. He's very active also in the privacy committee. So his contributions are continuing and continuing. And yeah, I know you already for a long time. And it's not only DNS-OARC, the whole DNS community is in depth with you. So thank you very much.
What he said, thank you.
Thank you very much.
And we have nice awards for the other three as well, so we'll send them to them in due course. Or actually, if anyone wants to carry them back, that would be really helpful. Okay, so we're going to break for coffee. Coffee is outside. Two things I'd like to do before we do that. First of all, the CFP for OARC 39 is now open. So the program committee has got that ready. So if you had an idea for a talk this week or over the course of this weekend, or you maybe didn't get a chance to submit this time, we're now ready for content for OARC 39 in Belgrade. The other thing is I would just like to thank our sponsors, in particular VeriSign, who are our workshop patron for 2022. VeriSign supports us in all kinds of ways, but their workshop patronage is really appreciated. And also a special thank you to Comcast. Again, Comcast support OARC in all kinds of ways, but they have directly sponsored this workshop. They have extended the IETF connectivity for 2 days to support us. They've been really helpful in just information about local facilities and helping us find the venue for the social this evening. So that's the first session. We managed to not completely drone on about all the OARC stuff. I hope you found it useful and interesting, and the whole team are here for the rest of the workshop if you want to ask us about any of that. And we will resume on time in just under 25 minutes at 11 a.m. Eastern from the coffee break.
All right. Hi, welcome to the second session of OARC 38. Thank you all for coming. This session, we're going to have 3 talks about experience with DNS operations, both internally and externally hosted. And the first 2 presentations are going to focus on experience with DNS-over-QUIC. And the last presentation in this session will talk about experience with very large zones on AWS. And this session is going to end around noon. Now, please welcome our first speaker, Andrey Meshkov, and his talk about DNS-over-QUIC.
Okay, let's do it then. Hello, everyone. My name is Andrey, and I'm a co-founder and the CTO at AdGuard. And more than a year ago, we launched the first ever public DNS-over-QUIC resolver. And today I'd like to tell you about our experience with it so far. But first, let me start with a very, very short introduction of what we do and where DNS-over-QUIC was deployed. So AdGuard is a popular content blocking available for all platforms, but also we do some DNS-based products. First of all, this is AdGuard DNS, a public DNS resolver, AdGuard Home, and AdGuard Apps, and all of them are able to use all kinds of DNS protocols. And DNS-over-QUIC they also can now use. And as I said earlier, AdGuard DNS is a public resolver with the focus on content blocking. And most of the clients are mobile devices, which is important to bear in mind because the patterns, the usage patterns are a little bit different for mobile devices from desktop devices. So where is AdGuard DNS now? Currently, we process about, on average, 1 million requests per second. And most of that comes from Android devices and DNS over TLS. But also we have like a considerable share of DNS over HTTPS, and now we have a small share of DNS over QUIC, but we hope it will grow with time. Now let's talk about QUIC. What is QUIC? Basically, it is reinventing TCP, but now it works over UDP and has some cool stuff built in. First of all, the encryption is built in. You can have a plain, you cannot have a plain quick connection. There will always be a crypto handshake, but this handshake will be faster than in the case of TCP plus TLS. Also, QUIC uses stream-based multiplexing, which also helps solve the head-of-line blocking issue TCP-based protocols suffer from. And finally, QUIC spec allows the so-called connection migration, which means that the client's IP address can change with no need to reconnect. Now let's take a closer look at each QUIC advantage. First of all, about the faster handshake and how it's achieved. Encryption and authentication are typically handled by a high-level protocol, but not with QUIC. As you can see on this slide, QUIC handshake combines the TCP-like handshake with the TLS handshake. And well, the important advantage of this is that it makes the handshake process faster as a result, since it now requires just 3 packets instead of 6. Well, it generally makes the connection faster. Now, the second point is the head-of-line blocking problem. And, well, this issue affects every TCP-based protocol. And it basically means that if there is any packet loss, the processing actually stops at that point. QUIC doesn't suffer from head-of-line blocking because, well, one of the streams may suffer from packet loss, but the other streams will continue to work. Finally, the connection migration. This feature, as I've already told you, it allows the client to change the IP address. For instance, a mobile client should be able to migrate QUIC connections between cellular and Wi-Fi. And this is achieved by introducing the concept of a connection ID carried by QUIC packets. Endpoints can use this ID to track connections that they're responsible for without the need to check for the source IP and port and destination IP and port and so on. Unfortunately, at this point, I am not aware of any QUIC implementation that fully supports connection migration. But I really, really hope that in the future, we will see some. Now, let's compare DNS-over-QUIC to plain DNS just to see why we need it. First and foremost, it's encrypted. But that's not the only advantage. Second, with QUIC DNS messages size is not limited by MTU, so no more need to truncate and fall back to TCP anymore. And finally, there's a built-in protection against amplification attacks. Well, I mean, there's a mechanism to verify the source address, so we're kind of protected. Now it's natural to compare DNS-over-QUIC to DO3 because, well, the current DO2 clients will eventually be upgraded to HTTP 3. And on the other, on one hand, it makes some sense to use DO3, but however, I don't see HTTP providing any advantage to DNS, and it just seems like a dead weight. So if we compare DNS-over-QUIC to DO3, both of them use QUIC as an underlying transport protocol. HTTP 3 adds HTTP on top of it, which means it sends and receives HTTP headers alongside every DNS query. Well, but protocol-wise, it adds no value. One could say you can benefit from HTTP caching mechanism, but why would you need to complicate things and use it instead of the standard DNS cache? And besides the overhead of carrying HTTP headers, it also adds more data points that could be used for example, for fingerprinting clients. And on top of that, all DNS-over-QUIC is a more complete protocol because it could be used not just by recursive resolvers, but also by authoritative servers, just like the good old plain DNS. Now let's talk about our experience with running DNS-over-QUIC on both server side and client side, and some simple insights. DNS-over-QUIC connections seem to be more stable and long-living compared to DO and to DNS-over-TLS. DNS-over-QUIC overall is heavier on CPU on the server side than both DNS-over-TLS, and it is pretty much the same as DNS over HTTPS. And well, clients seem to be a little bit more snappy with DNS-over-QUIC, probably because of a faster handshake process. Now let's talk about each of these points. The first one about quick connections being more stable and long-living. Here's how we measured that. We have a Prometheus metric with the number of TLS handshakes per protocol, plus we have a Prom metric with the number of processed queries. Dividing one on another, we can see that a different number of queries are processed through connections depending on the protocol. And first, we see that about 9 queries is processed through an average DNS over TLS connection. However, it's important to note that most of the DNS over TLS clients are Androids with Google's native DNS over TLS implementation, and this implementation has a very strict idle timeout. The connection will be closed if there were no queries processed through it in 7 seconds. So, well, it kind of explains why these connections like close all the time. With DNS over HTTPS, most of the clients are either AdGuard apps or browsers, so we can be sure that the idle timeout is not that strict. And we see that on average about 14 queries are processed through a single connection. And finally, with DNS over QUIC, we see that there are over 30 queries per average QUIC connection. So I suppose it seems that for some reason, QUIC connections are more stable and long-living. Finally, we tried to measure how heavy is QUIC on CPU. And well, since a single server responds to all kinds of protocols, comparing QUIC to others requires some tricks. Here's what we did. Processing a single query involves using different code in AdGuard DNS. Some of the code is related to the protocol. Some of the code is related to AdGuard internal logic. The AdGuard specific part is the same for all protocols, so we can use it as a base value and see how much overhead each crypto protocol creates. So we did some profiling on production servers and got some results. So let's take a look. And first, let's take a look at DNS over TLS flame graph. Here's how to read it. You should read it from top to bottom. The serve TCP-con function, the first column, calls read TCP message, then calls binary read, and so on and so on. The purple columns is the functions that are related strictly to DNS over TLS. And everything else is AdGuard specific code. And look at how wide the purple columns are and compare their width to AdGuard specific code. So according to this graph, about 40% of the time was spent in TLS related function. And let's take a look at DNS over HTTPS flame graph. The logic is the same. And the white central column is AdGuard DNS specific code, which we're using as a base to compare with other protocols. And according to the graph, about 60% of the time was spent in HTTP related functions. And now the same logic for DNS over QUIC. And again, about 60% of the time was spent in QUIC related functions. So overall, here's the results combined. You can see that both DNS over HTTPS and DNS over QUIC are heavier on CPU overall, which is natural because on top of TLS, they involve additional, rather complicated logic. But please note that it doesn't mean that with them a single query would be slower. Most of these additional operations are asynchronous, and processing a single query is still fast. And moreover, from the client's perspective, the protocol benefits may be more important than the increased server load. But yeah, both of them are a little bit heavier than DNS over TLS. It's important also to mention TLS session resumption. When a TLS session is resumed, the server certificate is not sent to the client, so the connection is established faster and fewer bytes are sent to the client. And what we see on our side is that DNS over TLS and DNS over HTTPS clients are able to resume TLS sessions in more than a half TLS connections. Notably, DNS over TLS clients show better results here, and it's hard to explain. It's hard to explain why. But well, with DNS over QUIC, the share of resumed sessions is really, really low. And probably this is an implementation specific issue, well, related to the library that we're using for QUIC, because, well, by the standard, it shouldn't be like that. But yeah, we have such an issue and we're yet to figure out what's the problem with this behavior and what exactly is causing it. Now to some mildly interesting insights that we're seeing on AdGuard DNS. And first, let's talk about request sizes and response sizes. Request sizes are pretty much the same for all protocols. So well, they are small, they are under 100 bytes. And response sizes, on the other hand, differ a bit. Let's see how. First, little heat map for plain DNS over UDP. Here's how to read this heat map. A very, very small share of responses are smaller than 100 bytes. Most of the responses are in the range of from 100 to 200 bytes. Then to DNS over TCP. Well, the situation is obviously a bit different because most of the truncated responses then re-requested over TCP, so it's natural to see that the responses are heavier here. Finally, DNS over TLS. Again, the situation is a bit different from the plain DNS because about a half of the responses are in the range of 100 to 200 bytes, and the second half is mostly in the range of 200 to 400 bytes. With DNS over HTTPS, it is again a little bit different. And there is a visible part of DNS responses that are larger than 400 bytes. It is hard to explain again, because in theory it should behave protocol-wise. It is not different from DNS over TLS. We should see the same stats. The only explanation here is that DNS over TLS comes mostly from Android devices, and DOE comes from iOS and desktop browsers. So, well, probably there's a different usage pattern here. And DNS over QUIC is the same as DOE. And again, we can only explain it because this metric is like device specific. One more mildly interesting insight is IPv4 versus IPv6. It is interesting that we see a much higher usage of IPv6 in the case of DNS over TLS Androids than in the cases of both DNS over HTTPS and DNS over QUIC. You can see on that slide that the share of IPv6 is about 30% for DNS over TLS, and for DNS over HTTPS, this share is much, much smaller. and same for DNS-over-QUIC. One more insight is the share of garbage DNS queries, the queries that we are unable to parse. DNS over UDP receives a number of garbage packets that we can parse, and this is, well, rather normal. What's surprising here is that the share of garbage DOE requests is also very high, probably due to bots that are sending HTTP queries to DOE resolvers. And DNS-over-QUIC and DNS-over-TLS are okay, almost no garbage. And finally, the last mildly interesting insight is the TLS versions distribution. In case of DNS-over-TLS, Android says a bit more than half of the TLS handshakes occur with TLS version 1.3. This share is much, much higher with DOE. And for DNS-over-QUIC, this share is obviously 100% since QUIC doesn't support older TLS versions. Well, I have finished with my mildly interesting insights, and let me introduce some DNS-over-QUIC implementations, just in case if you decide to use it. So regarding server-side implementations, one of them is a core DNS fork that we were using for AdGuard DNS, but we do not use it anymore. We are yet to publish the new code, but we will. And the part that is responsible for actually running the DNS server should be published with a permissive license, so any of you would be able to use it when we finally do that. Also, there's a DNS proxy. This is another tool that we maintain, and this is a very simple command line tool that allows to run a forwarding DNS server, just like DNS mask, but it also supports all kinds of encryption. And you can also use it as a library, by the way. If you write in Go, then it is rather simple. Also, AdGuard Home can also be a DNS proxy, which proxies queries to an encrypted resolver, or which runs as an encrypted resolver and proxies further queries further. And finally, ready-to-use DNS client-side implementations, all of which are, not all of which, but DNS proxy, DNS libs, and DNS lookup are published under a permissive license, so you can use it if you want it. And finally, thank you. I'm notified that I should finish. Thank you so much. Thanks for your attention, and I'd be glad to answer your questions.
Do you have plans for bringing DNS-over-QUIC to authoritative name service?
Not really. We don't have mostly because we specialize in running recursive servers, and we have no experience running authoritative servers so far.
Since it looks like DOQ sessions last longer, did you look at DOQ memory consumptions versus DOT or DOH?
Actually, this is what we haven't looked at because we were trying to measure everything on the production server. Yeah, it was rather hard to split DNS over QUIC from DNS over HTTPS and from other protocols. So no, we haven't looked at it, and this probably can only be done with the synthetic tests. So well, you can do it yourself if you want, using DNS proxy, for instance.
I will talk about our initial implementation of this. Anyway, thank you, Comcast, for helping us with this financially. And I will talk about the first lessons learned from this initial implementation, and also about the perspective for the future. So let me start with a special use case for this DNS-over-QUIC, and that is zone transfers. Zone transfers is a special communication that happens between different authoritative servers. So it's not about clients really, and they usually know each other in advance. So they can relatively trust each other, and they can be also configured in advance to have all the encryption keys and certificates ready. So as far as I know, there are no real hurdles in implementing DNS-over-QUIC for zone transfers. And the benefits are, of course, encryption. So the operators no longer need to operate, for example, IPsec tunnels to protect their zone transfers. And also the new features of the QUIC protocol, like multiple sessions per connection and so on. The alternative is DNS-over-TLS for zone transfers. They are quite similar in the use case, but QUIC has more modern features, so I would prefer that one. So in this way, I encourage all the vendors of authoritative DNS server implementations to implement zone transfers over QUIC. I encourage them, including myself. I have to do it. I hope Shia helps me to motivate for doing it as soon as possible. So with this zone transfers over QUIC being talked about, let me switch on to the normal operation of DNS-over-QUIC. This means to listening for normal queries from all over the internet, and this means that the authoritative server is now open to the hostile environment of the internet, and it needs to be like rock solid and prepared for any attacks that can happen there. So let me first summarize how the authoritative DNS server faces attacks using another protocols. So for DNS over UDP, it's quite simple because the protocol itself is really simple. It's completely stateless, so the only thing the attacker can do is to attempt to flood the authoritative server with so many UDP queries that it's not able to respond them all. And the server can do almost anything against it because it has no chance to distinguish between the legitimate traffic and the attack. So the only thing the server can do to mitigate this attack is to be terribly performant and be able to answer all the queries that come in. So yeah, this has been already solved in the last years by optimizing the DNS routines themselves so that the server does not take so much CPU per query, and also optimize the packet processing, because this was one of the showstoppers there. But this was solved by implementing the XDP technology, which moves the packet processing from kernel to user space, and it really saves CPU. And with this technology, we were able to handle tens of millions of queries per second in the optimal laboratory conditions. So we hope that this is pretty safe now, and the DNS over UDP can be operated safely. TCP is quite a complicated protocol. It's more complicated than you think. And it's not already really stateless. So there is wider range of attacks. The special attack is the SYN attack. That means that the attacker only floods the server with so many SYN packets, and the SYN packets are the first packets that are sent during the handshake. This can be mitigated in general by, for example, implementing SYN cookies. This can be done in firewall. There are many tutorials on the internet how to do this. And the more complicated attacks are different kind of resource exhaustion attacks, for example, slow lorries, which try to make the server allocate resources per the connection, for example, for the connection state and for incoming buffers for partially received data and so on. And they also use techniques that delay the disposal of those resources. And there are many of them. I just put them together into slow lorries because this is the most effective of the attacks. But in general, the server can protect itself by either by carefully configuring the kernel parameters for TCP connections, but this is difficult and it's not really designed for DNS operation, or by implementing a custom TCP stack that, for example, does not use the file descriptors for connections at all, because the file descriptors show to be really slow in multi-thread operation. So it has to implement custom TCP stack, custom connection tables, and there are built-in measures for avoiding slow lorries or for mitigating it somehow because it can be avoided. It also can be used with connection with the XDP technology, which again speeds up the packet processing. And with this all set up, it can handle up to millions of connections per second. So this is the defense against various TCP attacks. So when we were starting with the DNS-over-QUIC implementation, we saw that the protocol is quite similar to TCP. So we decided to take similar design of the DNS-over-QUIC authoritative server. We choose, so we are not DNS, and we choose libngtcp2 library, which I will talk about later. And also we use the custom connection tables with the similar measures against slow lorries attacks and similar. And since the libngtcp2 quick library is also in user space, so it was straightforward to use XDP for also user space packet processing. And the results about this all were really bad. We observed in our laboratory that the server is only able to handle like tens of thousands connections per second in this way. And the CPU was fully utilized. And from the profiler, we clearly saw even worse things than you see from the previous presentation, because in our case, we are an authoritative DNS server and our DNS routines are really optimized. So it was like negligible part of the CPU usage by the actual DNS, and all the CPU in practice was only used by cryptographic operations. And what was even worse was the memory consumption there, because in such a simulated attack, the server took like tens of gigabytes of memory for all the states and temporary cryptographic material. So yeah, we were kind of scared from this, because it opens the door for some attackers, but on the other hand, we are on the beginning, right? We just started our initial implementation of DNS-over-QUIC, and I hope there will be some development and further research in this, which shows the way out of this. So let us summarize the attacks that are possible against authoritative DNS-over-QUIC. The first is again the equivalent to SYN attacks. That means that the attacker floods the server with the initial packets. And this can be somehow handled by responding with the retry packet, which at least ensures that the source IP address is not spoofed, but it also adds one more round trip time to establish the connection itself. And if the attacker does not spoof the source IP address, it might not really help against this attack completely. And the other families of attacks like slow loris and similar, the only thing the server can so far, if we don't have another defense do, is to be simply more powerful than the attacker. And this means that it has to have more CPU for the cryptographic operations because they are like fighting face to face who is able to manage more connections, if the attacker or the server. So again, to say this, we are in the beginning, so this might improve in the future. So this is about attacks against DNS-over-QUIC, and let me tell you something about another features of the DNS-over-QUIC on authoritatives. As already in the previous presentations, you saw that the handshake in QUIC is somehow different. When the first time a resolver meets an authoritative server that it hasn't met before, they have to perform a full handshake, which consists of 4 packets. As you can see, the DNS answer is returned after 2 round-trip times, and there is a session ticket returned also from the server that the resolver can use later to initiate the next quick handshake. And with this subsequent handshake, the DNS answer is already returned after 1 round-trip time. But to complete the handshake, we still need another 2 packets to be sent to complete the handshake and also receive the ticket for the very next time. So I think that in some cases there are like 2 DNS queries, for example, for NS type and then for DNSSEC type. So it might actually not hurt at all. But in case there is just 1 query per connection, this does not mean that lower number of packets will be sent. But in any case, the quick handshake lowers the latency because the DNS answer is returned already after the first round trip. And the resolver has to remember the session ticket. But the authoritative server can be stateless in the way that not stateless per the connection, but stateless between those connections because it does not have to remember something. The session tickets already contains all the necessary information to encrypt even the first packet that is set with the subsequent query. Another feature of DNS-over-QUIC is the encryption. As we know, this helps privacy, of course. And the problem here is that then to establish the encryption, the client needs to validate the server certificate in order to know that it is talking to the correct server and not to the man in the middle. However, this is not like solved in the world yet because there is no signaling in DNS that would give the resolver possibility to gain the server certificate before contacting the server. So this is being researched by the deprived group in IETF, and so far with no clear results. So far the recommendation is to use self-signed certificate. The client shall not check this certificate, but anyway the connection is established, and when it's established then the encryption takes place and the connection is no longer unencrypted, at least. So now I will switch from the features of the QUIC to the features of our implementation. As I said, we are using the libngtcp2 library. It's the most popular library for C language. It is good for implementing the single quick connection handling. It takes care of all the states of the connection, which are really complicated in a QUIC. It also takes care about congestion control, so it's really cool. But it does not help with managing different QUIC connections. So if the packet is incoming, the implementation shall somehow find the relevant QUIC connection in its own implemented connection tables, and it also does not help with event scheduling, so that the implementation has to take care which quick connection needs to be focused on first. And it also needed some unnecessary code to really interoperate with the crypto libraries, but this is improving in the most recent version of the lib and GTCP2. So our implementation architecture consists of this library lib and GTCP2 and the GNU-TLS library, which is the crypto library that we use also for DNSSEC and other crypto stuff. And as I said, we use our own connection tables that are similar to our implementation of TCP on XDP. And we use XDP for packet processing, but as we saw that the packet processing CPU consumption is negligible in QUIC operation, then we are planning to also implement the DNS-over-QUIC in like the conventional mode where the UDP packets are handled by the kernel, because XDP has its own quirks that may be showstoppers for some businesses. So in any case, the implementation for QUIC on XDP is complete in the DNS right now. We have it in our Git master, and we are going to release it in the version 3.2, which is awaited at the end of the summer. And so far you can already try this. If you build Node.dns from master, you can configure for your configuration option, and you can try if it works by using KDIC, which is something like DIC but made by us. And it also implements QUIC, so you can make a query over QUIC to your authoritative server to see that it works over QUIC. And you can also measure it because we have another utility which is called KXDPGAN, and this is for generating traffic with the help of XDP. So with this you can generate traffic for DNS-over-QUIC against the authoritative server, and it will tell you how performant it is. I guess you can get back to those slides later, so I don't have to describe all the options. So to wrap it up, for authoritative DNS-over-QUIC, it brings encryption, and it brings very low latency, because in most cases the DNS answer is good after the first round trip time. And the performance seems to be good enough for all legitimate traffic. So it's good for the future. The thousands of queries per second seems to be enough for most real live authoritative server. The benefits of XDP packet processing are negligible, and there are issues that need to be fixed in the closed future, like the vulnerability to some denial of service and resource exhaustion attacks, and some other quirks like the problems with establishing certificates, which is not standardized yet. So thank you for the attention. I hope I end the lunch, and I'm waiting your questions.
Thank you, Libor. I think we have time for 1 or 2 questions. The first question is actually a comment by Victor, saying it may be possible to vend reusable session tickets and avoid sending a new ticket for each new connection.
According to QUIC standards, the session ticket is good only for establishing one subsequent connection, and for another one you need another session ticket. So it shall work like a chain of connections, that each time you use one ticket and gain another one.
The second question by Andrey. I don't get the point of using self-signed certificates. Why cannot the regular certificates for a domain name or for an IP address be used?
Yes, because in DNS the resolver works the way that it queries first the authoritative server of the parent domain, and then it gets the information that, hey, there is a new authoritative server for the child domain, and it only gets the name of that domain and one IP address that is in the GLUE record, so it does not have any possibility to have a certificate stamp of that server. So it's not possible to establish those certificates. And the point in using DNS-over-QUIC in this situation at all is that at least the connections, one is established, then is encrypted. So if the man in the middle is not actively just really in the middle, but is, for example, listening on the side, then at least against this kind of man on the side, the encryption is good, and it still brings some degree of encryption.
All right. Thank you so much. Everyone, please participate in the poll rating this talk.
Thank you.
Thank you, Libor. And please, there are some further questions. Please take them offline. Now, for the third presentation in this session, we're going to hear external DNS on AWS in large scale by Sidan and Sile Zhang.
So, hi everyone, I'm Sile Zhang from Salesforce.
And I'm Sidan from Salesforce.
So today we're talking about external DNS on a cloud environment in a large scale. So let's introduce external DNS firstly. So what is external DNS? External DNS is an open source application to make Kubernetes resource discoverable while public DNS servers. Kubernetes is an open source system for automating deployment, scaling, and management of containerized applications. We have hundreds of resources running on Kubernetes and need to be resolved from outside. External DNS is a good tool for us to manage their DNS records automatically and dynamically. To manage DNS records, external DNS would do the following steps. Step 1, it collects all required DNS records from Kubernetes resources. Step 2, it downloads all DNS records from matched zones from DNS vendor in cloud environment to its local containers. Step 3, it did some calculations between DNS records required by Kubernetes resources and DNS records already existing in zones. Then external DNS find the difference between its two and send change request to DNS vendor in the cloud. We use external DNS in a cross-account style. External DNS is hosted on service accounts and send API calls to accounts that host DNS zones. Generally, there are about 10 or 20 service accounts to talk with the DNS account that has the zones. Each service account has at least one cluster. So we need to consider scalability when there are more external DNS instances and the DNS updates. And this is common issue for everyone, a general scalability issue in DNS, because the cloud environment is everywhere and it provides limited resources. There are the maximum values for the resources, actions, and items that we can use in cloud environment. When your DNS services scales up to a certain level, you need to consider the underlying hard limit in your cloud environments. We will using AWS cloud environment as an example in our talk. AWS allows each account to make no more than 5 Route 53 API calls per second, and that's an unadjustable heart rate limit. And for Route 53 API calls, it only returns 300 record sets at once when you send a list request. And for zone size, AWS allows each zone to have no more than 10,000 records. This one is adjustable. The zone size will be doubled if we request a limit increase. So we can do a simple calculation. If a zone has 10,000 records and every record is a separate record set, it needs to at least 34 list API call to Route 53 to retrieve the whole zone. So we can observe an issue here. External DNS downloads all DNS records of matched zones. And if zone sizes are big, external DNS consumes a lot of API calls in one run. And in our real operations, we have multiple external DNS instances and zones that have more than 10,000 records. Throttling error happened there, and our service is blocked in DNS updating. So one thing in external DNS design can even make its situation worse is external DNS generally creates 2 DNS records for one endpoint of Kubernetes resources. It creates one record set for DNS resolution, like alias, CNAME delegation, and another TXT record for DNS ownership management. Its design doubled the zone size and increased API consumption. It brings challenges that we need to overcome when DNS services scale up in real operations. The first challenge is the number of records in hosted zone reach the rate limit. And the second challenge is the API throttling issue. And Sidan will introduce more detail for these 2 challenges and how we resolve these 2 issues in real.
Thank you, Sile. Can you change to the next slide, please?
Sure.
Yeah, so the first challenge is the zone record limit. AWS has a default limit on hosted zones, which is 10,000 records per zone, and it's adjustable. If the hosted zone reaches the limit, it will block new Kubernetes resources from creating DNS records in the zone. The impact is critical because services cannot be queried or deployed without correct DNS records. As this quota is adjustable, our solution is to create appropriate monitoring and alerts regarding the hosted zone size by Python Lambda and request a higher quota when receiving an alert. The Lambda sends real-time zone size to AWS CloudWatch metrics every minute, and the alert is generated when the number of records reaches 80% of the quota. At the same time, we reduce the zone size by applying sync mode in external DNS, which allows for full synchronization of DNS records and removes stale DNS records. Next, please. And here is an example of modifying the policy of external DNS from observed only to sync. External DNS is highly configurable, and we can control how records are synchronized by modifying flags in deployment manifest. And next, please. And the second challenge here is Route 53 throttling issue when multiple external DNS instances are running that exhausts all the API rate limit, which is 5 calls per second. If Route 53 can process the request before the next request for the same hosted zone, it will reject subsequent requests with an HTTP 400 error, causing failures to external DNS. Here, our solution is about zone size reduction and enhancement of the cache mechanism. Firstly, applying sync mode to external DNS reduces the zone size. Consequently, it decreases the number of API requests as fewer records are to be downloaded in one external DNS run. Following that, we adjust the external DNS synchronization interval from 1 minute to 10 minutes, meaning that external DNS will check for update once per 10 minutes instead of the default 1 minute. So there are fewer external DNS requests. Next, please. So here is an example of modifying the polling interval. Increasing the interval will not affect your service. However, it will mean that a DNS won't be created until the maximum of the interval. Next, please. So here are the 4 takeaways from our talk today. Firstly, somewhere in your cloud like AWS or Azure, you may use Kubernetes with external DNS in order to make your service discoverable via public DNS servers. At the same time, be aware that external DNS is not distributed or scalable. Therefore, you might be careful about the underlying rate limit in the cloud. Finally, for AWS users, if your Route 53 talks to multiple external DNS instances, it might be a good idea to scale your system horizontally by creating subzones in multiple accounts. All right, that's it. It's our pleasure to take any questions now.
Yeah, I see there is a question. Is there a way to optimize using zone transfers from AWS? Just let me clarify. Do you mean using external DNS to do the zone transfer in AWS, or are there options we can use for zone transfer in AWS? Yeah, if that's the first one, external DNS doesn't do anything about the zone transfer thing. It's a tool for like the automatically manage the DNS records that you need for a Kubernetes cluster. And if you want to do some zone transfer thing automatically and programmatically, you need to use the Route 53 API things. So that's two different things.
Thank you, everyone.
Hi, everybody. Welcome back for DNS-OARC. We are going to start with session 3 of day 1. To the mic. So yeah, we're going to start with session 3 of day 1. We're going to have a mix of operational and analytics talks this afternoon. And there was a slight change in how we are going to do Q&A. To do Q&A when the speaker is remote, everything will be done through the chat by preparing questions with questions, hashtag questions. When the speaker is in person, people can go to the mic and do their question there, and questions from the chat will be relayed to them. Niels will be doing the timekeeping this afternoon, and I would like to thank Comcast and Verizon for their sponsor. And with that being said, we're ready to, just one more thing. Please, when a talk is going to be started, there will be a poll that comes up. Please answer the poll. It helps us get a better understanding of what you like or what can be improved. That being said, I'm going to pass it on to Brett, our first remote speaker of the afternoon.
Thank you all for letting me speak at OARC again. I want to talk this afternoon about transitioning DNS for GTLDs, and in this case, what I mean by transitioning is moving DNS and registry systems from one registry service provider to another registry service provider. So this is an existing GTLD moving between providers. This is the agenda I'm going to go through. I'm going to talk a little bit about Nominet's DNS team and systems, our relationship with GTLDs, talk about the different stages of transition, and move on to a couple of other topics at the end. So the Nominet team are a team of 6. The DNS team are a team of 6, and we support the following services. We support AuthDNS for UK, AuthDNS for 67 GTLDs. We operate a recursive protective DNS service for the public sector in the UK, a private network service, DNS recursive service for the public networks in the UK, our own obviously internal corporate DNS, and lastly, something we're trying to do a little bit more of these days is some engagement with the DNS community on protocols, policy, and operations, etc. And that's obviously one of the reasons I'm here today is to try and up that engagement a little bit. Nominet are very aware that they stepped back from this in the last few years, and it's a new strategy for us to engage heavier in the community. So hopefully you see more of me and some of my colleagues in the future. So Nominet are currently the registry provider for 2 GTLDs, .Wales and .Cymru, and we are the back-end registry service provider for 67 GTLDs for various different customers. We're also one of the 3 global EBRO providers. EBRO is Emergency Backend Registry Operator. So we contract with ICANN to be able to take GTLD on within 4 hours notice, basically. So what I want to talk about today is transitioning GTLDs, the experiences we've had is transitioning GTLDs in from other providers and out from ourselves into other providers. And this we kind of developed, well, because we've done a lot of these over the years, we've developed a kind of process for doing them, and what I thought it was worth publicizing that process a little bit and trying to maybe develop it into some kind of best current practice or standard in the future for everybody's benefit. So in phase 1, we're notified of a new GTLD order from our colleagues in our registry sales department, and we initially do some assessment of the size and impact of that GTLD, because obviously there are many sizes of GTLDs out there, and if we suddenly had to take something on the size of .com, for instance, that would be a very different matter than taking on something that's got very few delegations in it. So we make some assessments, and those assessments lead us in a decision about where we deploy that GTLD in our infrastructure. We've got a standard process where we put most GTLDs, because most fit into a size. Most of the ones we've ever taken on fit into a size bucket that makes them all deployed in the same way. We build some test infrastructure, and we do lots of testing. We have a policy that basically says everything we do in production, we do in a test staging environment. So we build that test infrastructure, we build the production infrastructure. And this doesn't necessarily mean we build new infrastructure for every TLD. Some of it's maybe just modifying existing infrastructure. And every one of these build stages is, as you would expect, documented and defined as code. In our configuration management tool, we use Ansible exclusively for that these days. The build at this stage is made up of what will be surprising to you, I guess, of a registry database, some provisioning infrastructure, some DNS-SEC signing infrastructure, some distribution servers, and then two different types of DNS sites. So we operate some in our own data centers, which are highly available with lots of bandwidth, etc. And then we've got some sites that sit in the cloud. And some of you may have seen presentations that I've done in the past about our cloud-based infrastructure. We create an initial dummy zone file and add relevant records, and add plenty of monitoring to make sure that we know if anything's going wrong, and then we hand it over to our colleagues in QA. And once QA have looked at it and signed everything off as working properly, we then schedule RST. For those of you who don't know, RST is abbreviation for Registry Systems Testing. This is a process that's done by ICANN as part of a transition. So ICANN do various standard tests across the whole infrastructure to make sure that you're ready and fully tested to make sure that you're able to run that TLD. So the ICANN engineers test various things like DNS servers that are responding properly, zones are properly DNS-SEC signed, EPP, who is an RDAP, working properly, and where required, IDNs have been set up with in the correct way. If they find any issues, they raise a ticket with us, and we've got to fix those fairly quickly. There is a charge for RST, and if you don't complete it the first time, you get recharged again. So if you fix the issues fairly quickly, then you don't get a recharge for it. RST, depending on the complexity of the GTLD in question, usually takes 2 to 3 weeks. And I'm glad to say we passed first time every time we've done one. But the problems are much less now than they used to be, because we're used to doing them now. We then move on to phase 3, and this is where we start doing the actual DNS and DNS-SEC transition. So at this stage, RST has passed. We're working in a current state where the incumbent provider, so the old registry service provider, is producing and distributing the zones. Nominate is producing and distributing dummy zones, and at this stage we make a change so that Nominate ingest the current zone from the incumbent. We unsign that zone and re-sign it, but adding the existing public keys, so that when we do the transition, we're post-publishing and we distribute it to our new infrastructure. So in other words, we're taking the zone taking the existing zone on a continuous basis using notifiers and XFRs, taking all the DNSSEC information off it, but adding or keeping the existing public keys in there, and then we distribute it out to our public infrastructure. But obviously, at this stage, it's still it's not live at all. We then generate using a standard script that we have with various change files. These have clear dates and instructions to the incumbent provider because there's lots of work needs to happen by that old provider at this stage. And so these change files have the instructions of exactly what they should do and when they should do it. And there are 6 files in total. The first one instructs them to add the nominate DNSSEC keys to their existing zone, in other words, to pre-publish them, to add the DSs for the NIC, TLD and TLD, to add the DS records to the root for the new keys. The third one is to add, we then once the DNSSEC keys have been published for long enough, we add in stage 3, we add the name server entries for half of the new name servers and remove the NS entries for half of the old name servers. So we do this in a staged manner. Then there's a time gap, and we then add the NS entries for half of the new name servers to the root using the root zone management system, and again remove NS entries for half of the old name servers from the root. In steps 5 and 6, we repeat steps 3 and 4 for the second half of the name server, and obviously at this stage, Nominate are now taking all the DNS traffic. We often at this stage also update the admin/tech contacts. This isn't the same for every TLD because it depends what the registry themselves want to do. But generally speaking, we find that the registry want to keep hold of the admin contact, and they give Nominate the tech contact, and that splits any future changes between 2 organisations, which makes it secure, obviously. So at this stage in phase 3, the current state is that Nominate's name servers are now in the zone and the root, and we're getting all the traffic. DNSSEC is signed by Nominate, but we're publishing the incumbent provider's old keys. The zone is still being provisioned by the incumbent, so the TLD at this stage is dependent on both providers because they're still taking new registrations and changes, pushing them into the zone file using provisioning at their end, but then feeding the zone for us to serve it from our name servers. The phase 4 is the actual registry transition itself. So we fix a date in conjunction with the old provider for a date of the transition, and they publish registration downtime so that any registrars know that for a certain period on a certain day they can't do any changes. On that day, the incumbent operator makes the registry read-only. They produce a database escrow file. This escrows are produced every night anyway because it's part of the ICANN registry contract is to produce escrows and push them into an escrow agency every day. So this is a commonly done known process. It's just normally it's automatically done each night and pushed into an escrow. But at this stage during the transition, the incumbent provider produces an escrow file while the registry is frozen and supplies that to Nominate. Nominate then populate our new registry database using that escrow, and we generate a new zone file from the new database. That zone file is checked and loaded into our infrastructure, and then once we're happy with it, and it's gone through various checks and balances and QA, excuse me, it's our DNS-SEC distribution infrastructure is changed, so it's switched over to use that new Nominate generated zone file. And then in phase 5, we do various cleanup activities. So after a certain period, obviously we can remove the old DNSSEC keys from the zone we're publishing because they're no longer required. Remove the extra DS records that are no longer needed from the parents. And the incumbent can obviously, we then can remove the incoming zone from our infrastructure because we no longer need it. And at that stage, we're done. So what else? Other things that happen. We obviously do. We've done many transitions in. We've also done some transitions out. What we tend to do with transition outs is let the new provider lead the process. We often talk to them about the process that we've got and encourage them, but we don't mandate it. The way we view it is that the gaining provider leads the process. But if the particular provider in question isn't experienced, we'll happily guide them and to use our process. We have a slightly different process for DNS transitions that are out of bailiwick, where they are transitioned onto a different set of name servers temporarily. But again, that's a known process that we've done several times, because obviously some providers have the name servers in within the TLD, like we do. All of our name servers are within nic.tld, but some providers don't, which makes it the process slightly different. For future plans, we've got a lot of automation in this system because we've done it a lot of times over the years. But there are obviously from time to time variations in the way that things work and the way that other operators want to do things. And obviously this means that not necessarily everything can be automated, and sometimes changes to the process have to be made. So we want to try and standardize this a bit a lot more and make the deployment and changes automated as possible with automated testing, etc. So that's something we want to do more of in the future. Before I move to questions, and a couple of points, end points I wanted to make here is we've obviously done these transitions with many different providers over the years, and I won't call those people out, but what I will say is just about, well, almost everyone we've worked with on transitions have been extremely professional and worked with us in a really good manner, and that's not to be understated, because obviously it's a situation where somebody's lost some business, so you could imagine they might be a bit sore about that. But we've seen nothing but professionalism when we've been doing these transitions in both directions. So I think that's a testament to the industry. One late breaking thing on this presentation, that we're actually in the process of doing a transition at the moment, and what we've found is this one hasn't gone quite as smoothly as normal. We've had some question marks in the way we're doing it, which has led us to change the process slightly for this particular transition. And that's kind of gelled something in my mind a little bit that makes me think, well, is there some work that can be done here, maybe to try and standardize this process, to create some kind of best current practice document or something like that, so we can point different registries at with different levels of experience of doing this, to say, this is what the industry recommends as the way to operate this process. And it's certainly something I'd be interested in working on. I think I'd like to get help from other providers who've had similar experiences to author that kind of document. And I'm not 100% sure where that document should live. I mean, my initial thoughts are maybe it could be some kind of BCP RFC, but I don't have experience in that area of writing RFC. So if people, one of the things I wanted to say is, I'm happy to hear questions, but I'd also really like to hear feedback and comments on the idea of making this a BCP or something like that. And that can either be now in the Mattermost chat, or equally if anybody wants to approach me afterwards directly, then I'd be happy to have a chat about it. I was actually supposed to be in Philadelphia today, and wanted to pick up with people directly on this. Unfortunately, my wife got COVID 2 days ago, so I was at the last minute not able to travel. Anyway, on that note, I'll open it up to questions, and I'll have a look on Mattermost to see if anybody's got anything. Thank you, everybody. Quite a lot of questions. So Duane has asked, what would you say is the most stressful aspect of a transition in? I think when we were first doing this, it was kind of, because it was unknown, and we were, obviously worried about breaking GTLDs. And I think probably in those days, the most stressful thing was making sure we did DNS-SEC properly, because it felt like that was the most brittle part and the most unknown part. But I think that has largely gone away due to the amount of times we've done it. These days, I would say the most stressful part is if we get something from another provider that says, well, we don't want to follow your process. We've got our own ideas, and once that change to the way we do things gets introduced, that introduces doubt and risk, and therefore that can become stressful. Question from Jeremy: can you reveal how many such transitions did you go through? So of the 67 TLDs we've got at the moment, I think 65 of those were transitions in. I think about 35 of them were done in one go, so it was 35 from a single provider. The rest of them were individual ones. We've also done about, I think it's probably about 5 or 6 individual outbound transitions, and also a group of 30 in one go as well. I hope that answers your question, Jeremy. Hazel has asked, you mentioned that you're an eBro operator. Is this something that you normally have had to do often? Anything in particular that stood out to you from participating in emergency transitions of GTLD zone operations? We've been an eBro operator for probably about 7 or 8 years, I think, and in that time we've done one live transition. We do practices several times a year, so we're well practiced in doing it. And actually, we made a lot of changes recently to add automation using Ansible. So we've recently done a practice in literally about 3 weeks ago, because we added a lot of Ansible automation. Anything particular that stood out to you in particular emergency transitions? I think what stands out really is the fact that we have to transition DNS in within 4 hours, which obviously means you've got to really have the operations automated and well practiced. You get 4 hours to do the DNS and DNSSEC transition in, and you get 72 hours to bring the database in. So I think that is the thing. Brian Dixon has asked, presumably the entire procedure can be backed out by reversing the steps at any stage. Have the rollback procedures ever been tested on a live TLD? Good question. Yes, I think we could back it all out. I think we designed it that way. No, I don't think we've ever tested it on a live TLD. Obviously, that's difficult to do on a live TLD. Maybe something we should talk to ICANN about at some point is having a test TLD in the route to do this kind of thing. I think that would be really, really useful, because every time we do a test, we do it on a test TLD that's not in the route, which obviously is not completely completely the same as doing it for real. Chantra has asked, assuming those transitions do not happen very often, do you run mock transition to ensure the process will not break from one transition to the other, and that operator will not cause incident? Yes, we do mock transitions using an example TLD multiple times a year. We have a team of people, and we have a team of people that work to manage these, and a team of engineers that work on them. And every time somebody leaves or is added to that group, we want to test, basically, and that happens, multiple times a year. Paul says, not a question. Please don't write this in the ICF. It's an ICANN process. Paul, I'd really appreciate a chat about this afterwards. So I'll drop you an email. PMFZEC question. I've got a feeling I'm running out of time, so I'm going to go quickly here. Since the transition has obvious possible consequences on resolutions, could it, shouldn't it, be addressed in the term of best practice document, etc., by ICANN Security and Stability Group, even if it is strictly for GTLDs, but can be used for inspiration by others? perfectly happy to talk to SSAC about this. If people think that an SSAC guidance document on this would be better than an IETF BCP, I'm perfectly happy to. I know people in SSAC, so if I'm perfectly happy to approach SSAC about this. Question from Victor. I didn't see you mention freezing key rollovers on both sides during the transition. Of course, the algorithm on both sides needs to be the same. Yeah, so that is in our process. I didn't mention it. You're right, Victor, but we do check the algorithms to make sure they're the same, and we do mention to the old provider that they should not do any key rollovers, and we have systems in place to check that key rollovers aren't happening. Question from Pala. Did you take time gap between steps into consideration when you pre-publish and publish the DNS keys? Yeah, one of the things that we do in all of those files that we produce to tell the incumbent operator what operations to do is there's clear time guidelines in all of those bits to say stop this at this stage, stop and wait this amount of time and don't carry on until this time has disappeared. And then lastly, Rick has commented, I don't think this is scope for SSAC. So I've had somebody say it's not in scope for SSAC. I've said somebody say it's not in scope for IETF. I'd really like to get somebody feedback on what people think it is in scope for, and feel free to drop me an email or a Mattermost message on that. Thank you very much, everybody, and I'll let the next speaker get on.
Here's the agenda for the presentation. There'll be some background around DNS cache poisoning, what kind of issues there are, and what mitigations are available. Then some summary of how Google Public DNS operates at a very basic level, and then the countermeasures we have implemented and how well they have worked and what coverage we get. And I'll conclude with some remarks on our effort and what we think could be done in the future. So RFC 3833 was the first one way back in the 2000s which discussed this issue. There's a number of ways that DNS queries between the resolver and authoritative could be attacked and bad answers populated into the cache. And of course, the easiest one, if an attacker can do it, is being on path. If you're on path, it's essentially game over for UDP queries. And unless you are able to encrypt the transport, there's nothing to be done. The other one, which the Kaminsky attack pointed out, was passive spoofing. And as long as you can guess the query and get an answer to be accepted by the resolver, that can result in a successful attack. There are others listed there, but those are not the focus of this presentation. As I just mentioned, most of the spoofing is relevant for UDP because it can be done off path. It really just requires the attacker to generate a lot of fake responses which are likely to match the queries which have been sent. And the conditions for a successful spoofing, you have to either be able to force queries, which is relatively easy to do, or you have to guess when a resolver is gonna send a query by some other means. And for a response to be a fake response to be accepted as the real answer, it has, of course, to match the question section, the query ID in the DNS query, and the destination address and the port, basically the 5-tuple in terms of TCP IP. And of course, the response has to arrive before the real answer arrives. In that case, if the authoritative is further away from the resolver, that makes it easier to get the fake answers into the cache. I've basically taken what's mentioned in RFC 5452 in terms of the math and the probability of an attack being successful. I'm not going to get into the math, but the key point is that based on what was common in the mid 2000s, I believe,
and if you were not randomizing the source port, it was very easy to spoof a response. And if you were using short TTLs because you wanted to be able to change answers faster, the attack window was even significantly wider. And yes, as the slide says, you had a 50% probability of succeeding within 3 hours, which is pretty bad. And so RFC 5452 also described some countermeasures to protect against the attacks. And at this point, I believe most stacks implement this. So we are reasonably well protected against attacks. The most important one here is randomizing the query ID, because the query IDs should be randomized, and that's 16 bits. And in addition, using the different source ports for any pending queries. Between the two of them, that gives you about 32 bits of protection, give or take. And as the math on this page shows, the probability of an attack succeeding significantly goes down. So generally speaking, if you're not a large service and there are not other considerations, this gives you most of the protection. And also to add, since that RFC was written, there's a couple more things which can help us with protection. One is, of course, DNS cookies, which after the addition of making sure that they are compatible across different platforms or different implementations, that gives you 64 bits of protection, and that makes it even harder for anyone to spoof responses. In addition, while we talk about authoritative DNS over TLS or DNS over QUIC, for privacy reasons, it of course helps prevent spoofing attacks too. Okay, just a quick summary of Google Public DNS in terms of how our resolution works. The resolver, as people here mostly know, it's replicated across a lot of metros around the world. And in each metro, again, we have a reasonably large number of servers, easily in the tens, maybe more than that. And that means that while we dedupe queries, outbound queries for the same name and the same type on a single server, since we like to run this service without having shared cache across servers, we do not deduplicate the requests across multiple servers. And the additional thing we have is we use eDNS client subnet to geo-target answers for different client IPs. That again expands the range of queries for the name and RR type, which could be pending at the same time. So these two things combined means effectively we can have a lot of queries pending at one time. And in the sub-bullet there, that is, I think, the weakness which is there is that an answer to an eDNS client subnet query without ECS in the response, which again shrinks back the random bits in the query, can be used to match against any of the pending ECS queries. And for obvious reasons, I've not put any math here, but this does increase the exposure that Google Public DNS has for spoofing. Okay, so if you just start looking at this, the obvious thing would be that let's implement the RFC 5452 countermeasures and do DNS cookies, and we are done. Unfortunately, like a lot of things on the internet, it's not as simple as that. Before we did cookies, we went and looked at what is the coverage for cookies and other features on the authoritative servers. Okay, a little segue here to how we determine that. We look at our outbound query logs to figure out what are the top name servers in the world, the live ones. If they're dead, it doesn't matter. And they're getting a reasonable amount of query volume. And we take the top 1 million servers, and we run probes for various DNS features to them from our data centers in central US. And here are the numbers. For comparison, basically also showing the numbers for eDNS0 support and ECS support. And you can see, as you can see, DNS cookies are supported for really only 12% of the outbound traffic we have. Even though that looks bad, I think there is hope in the sense that ECS is supported by about 48% of the servers and about 95% of the traffic volume, which means that these servers are relatively new. These are not operators running really, really old code. So it should be relatively straightforward if they want to add DNS cookie support there. Okay. So now we'll talk a bit about the countermeasures that Google Public DNS has implemented. We do most of what's mentioned in RFC 5452. In addition, we have implemented support for DNS cookies. At the moment, due to some issues which we encountered, which I'll talk about in the later slides, we have not enabled it like fully or in an auto detection mode. We've only enabled it for a handful of large servers where we are sure that the implementation is working correctly. In addition, we also implement case randomization, which is described in an expired draft linked here. And as the slide shows, it's very basically if there is a letter in the name to be queried, you randomly flip the bit on it. That basically gives us a few extra bits of protection. And for names which are within a registered domain, this will assume something like google.com. It'll give you 10 bits of randomization in the query. Of course, it's not very useful for root or TLDs because there really are not that many letters in that. In addition, as some of the root operators have noticed, we will, for queries to root and TLDs, we prefix them with a nonce, which is, it is 64 bits, and we use that again gives us more protection for queries to the top of the DNS tree. Okay. And yes, at the moment we do perform DNS over TLS either by manual configuration and over the last few months by unilateral probing. And for the two, we use slightly different ways to decide how much traffic to send over them. For manual configuration, we will send all the traffic over TLS, except if we hit issues, then we'll fall back to UDP. And for the ones where we are detecting DOT is available by probing, we are much more conservative. We'll try to balance equally across UDP and TLS there. And this is primarily because we don't have a good idea how much query volume the servers could support. And the results are encouraging both for manually configured DOT as well as for unilateral probing. We can see that usually DOT is by a very small percentage better than UDP in terms of success rate. And latency-wise, it will be within, it's variable across operators, but it's within the statistical margins. Like, for example, I can quote for one of the root servers, it's typically like 1.9 milliseconds over UDP, and for TLS, it's within 1.9 to 2 milliseconds. So we are not seeing any significant latency increase there. Okay. Okay, and this is about, okay, we do these mitigations, what do we do if we detect a problem? And generally, the times when we see a suspicious response is small enough that we fall back to retrying over TCP, and that usually works as long as the domains do support TCP. Thank you. And for TLS, there we just load balance queries or retry across all the name servers and endpoints we know for that zone, and it's the usual what do you do when a query to a name server times out. It's that level of retry for TLS. Okay, so this is kind of the fun and frustrating part of doing anything on a large scale. It's really to give a flavor of the kind of issues we encountered when we implemented these countermeasures. So for when we did DNS cookies, the most common issue we see is that the name server responds with a R code which is not success, and if we are also doing ECS to the same name server and we haven't confirmed support for either of those two protocol features, then it's very hard to determine, did the server not like option DNS cookie or ECS or both, or something else happened. And so the signal, it's a much harder signal to get out of that. And the problem is the query volumes may not be high enough to that name server to build a signal easily over time in a short period of time. So, and the bullet number 3 is the one which is most problematic for us, is that sometimes some name server will mostly be responding with DNS cookies, but once in a while, occasionally, they will not send us back a cookie. And it doesn't look like an attack, meaning from our analysis, but it just, they don't respond with a cookie. And that's very hard to disambiguate in the real world from an attack. We can only guess why it's happening. Maybe their anycast is not stable, or they're running multiple implementations in the same data center. Again, case randomization, again, we hit some issues, but the situation is better here in the sense that fewer number of servers are affected by the problem. And the most common one is that the case randomization is lost in the response. But there's still a very small number of cases where we do end up, the server thinks this is not a valid name, and therefore it responds with a failure code. And the other thing, I thought I would just mention it, and this was also what triggered the thread yesterday, is once, due to the specifics of our implementation, if a UDP response is truncated and it's malformed, we are considering that we'll just throw away that response, because it can happen that, for example, the DNS cookie in the options may no longer be present if the response is malformed, and we lose some of the protection that way. So we made the decision to drop those packets, and it interacts badly with our case munging when we go back and double check that the name is okay. Okay. So this slide, I think, is the key slide here. It talks about what kind of coverage we can get if we were to maximally deploy all these protections. And again, the ECS and EDNS numbers are there just for comparison. DNS cookies, unfortunately, will only give us about 12% of traffic protection. There are a number of root and TLD operators who have started supporting cookies. So thank you. That's where I think the value of cookie protection is the most. And the good news, though, is that with case randomization, we can get to about 99% or so of the traffic volume over UDP, which is great. And DNS over TLS, even though it's still early days, signaling has not been worked out, and only a few operators are doing it. But we do have about anywhere from 4 to 7% protection, depending on which servers are up and running on a certain day. All right, some concluding remarks and suggestions, and then we are open for questions. So the main point, I'll not talk through all the numbers here again, but the main point is if we look at the set of countermeasures that a resolver operator could deploy and use, you can get, even with UDP, you can get fairly close to like 95, 99% of query volume being protected, which is good. Meaning, ideally, of course, we all want to move to encrypted transport, DOT or DOQ, but until that happens, having these other countermeasures in place is valuable. Okay. So these are the things we are planning to do in the short and medium term in this space. Basically, since we have found the DNS over TLS will continue doing more as time goes by, and as more operators enable it, we'll have that. I conspicuously left an empty bullet there. This is, I'm sure someone will ask, signaling. I think that's a much broader topic, so as and when work happens in that space, we'll be collaborating with others, but I think it's still too far out to bank on that in terms of having a real impact in production. In addition, we will like to do DNS cookies and case randomization more aggressively and cover more traffic. And nonce prefixes are kind of a somewhat, I wouldn't call it hacky, but still a non-standard thing. So as we get more cookie protection, we would probably turn it off where we can safely. And some recommendations for authoritative operators. Of course, if you can implement cookies, which I believe most operators should be able to, because it's really a small feature on top of the other DNS protocol features. If you can, that's add 64 bits of protections. It's relatively straightforward. If you do that, it will increase protection for everyone. And of course, if you can't do it, or even otherwise, please follow RFC 8906, which has a lot of common sense advice on how to respond to queries you may not be able to answer, or otherwise, or features which are there in the query which you don't support. It really helps resolver operators know what an auth server supports and behave accordingly. And yes, if you can do DNS over TLS, if you can justify the overhead that DOT or DOQ introduces, please do start experimenting, because it will solve not just the cache poisoning problem, but provide better security for all communication between resolvers and auths. And we are happy to experiment with anyone else who's thinking of doing that. Thank you. And I'll take questions.
There were a few questions maybe from that were asked a while back online. So I'm going to start with Christian. Elmirot asked, are there plans to support DOQ against auth name servers via unilateral probing or some other mechanism?
So we would like to support DOQ, but a number of things need to fall in place before we can do that. So I guess the answer is yes, but nothing to announce yet.
Brian Dixon is asking, maybe the cookie non-response is different backend servers behind some kind of load balancers.
Potentially, yeah.
Hi, Niels from DSEC. I'm wondering if Google Public DNS accepts fragmented packets, and if yes, if there is some mitigation against fragmentation attacks.
Yes and yes, in the sense that basically at the network edge, basically they have put in common sense rules to protect against that. One simple thing is we do not, I believe, handle I'm forgetting the word for it, but the ICMP message which comes back and says packet too big, because we know we don't set big packets and we don't expect something which is bigger than Ethernet. So we reject those ICMP messages because most likely they're going to be trying to be associated with poisoning attacks.
Hi, John Todd with Quad9. Really pleased to see you supporting DOT. What are the plans on the opposite side? When is Google, or is there a plan for Google to support DOT on the authoritatives, and is that going to scale across all of your domain properties or just some?
So I think I'll give the same answer as DOQ because we want to do it. There's a number of things which need to fall into place. So to give a little more detail there, I don't think initially we'll do it for like google.com or like youtube.com, but for cloud DNS customers, that will probably be the first place where we start.
Great, thank you.
All right, and our last question from the chat that doesn't need an answer in this session because it's not related to DNS cookies anyway. Will it be reasonable for Google to provide some regular reports of the top 1 million domains queried now that Alexa 1 million has been officially retired by Amazon? Many researchers use lists like that as a metric.
I think here we'll have to check with other groups within Google, meaning we may be able to share some of that, maybe not million, but I can't promise anything here. I would say please contact us offline.
Cool. Thanks a lot, Puneet.
Thank you.
All right, so let's move on to our next speaker, who will be remote. This is going to be Zhang from Salesforce, talking about how an enterprise manages very large number of records.
Hi, everybody. My name is Zhang. I'm working on the DS team at Salesforce. And today I'm going to talk about how a large enterprise manages a very large number of DS records. And we are from different companies, organizations, universities, and we use DNS in different ways. So I think we can ask ourselves a few questions. For example, who make DNS changes in our organizations? Are the DNS teams the only people who make DNS changes, or we have different operational teams that make manual DNS changes, or we have some code or tools that make automatic DNS changes? And how many zones we have? Maybe we have tens of zones, hundreds of zones, or thousands of zones. And how many records we have in these DNS zones? Like thousands or hundreds of thousands or millions of records there. And maybe the zones, some of the zones are dynamic, which means the records in the zones are being changed every single second, or the records in the zones are relatively static. Maybe they are changed every few weeks or even every few months. If we have many zones, maybe we host all of them on single DNS provider, or we host them on multiple DNS providers. And if we do host them in multiple DNS providers, how many accounts we have on each of them, and how many accounts we have on all of these DNS providers. And it is, it could be some operational overhead to manage all of these accounts on multiple DNS providers. And things get complex when we have tens of millions of records in thousands of zones, and if the zones are hosted on multiple DNS providers. So if this is the case, it is almost not possible to make manual change because it doesn't scale. It is not manageable. But a bigger problem is now all the end users. So by end users, I mean the DNS teams or operational teams or automation tools needs to know the DNS details of the zones and the DNS providers. And these multiple DNS providers do use different REST API specifications. So for example, if the tool or a team wants to change a record in Salesforce.com, maybe Salesforce.com is on provider A, and then this tool or the team needs to send the REST API specifications of provider A to this specific provider. And maybe in the next minute, they want to change the records example.com, and then this example.com is on provider B. In this case, the end users need to talk to provider B by using the corresponding REST API specifications. So the things get more complex if we add new zones or if we migrate zones between multiple DNS providers. Because we have to add or change all these zone vendor mapping logics between in all the end users, like the teams or the automation tools. So in summary, if we let the end users handle all this detailed knowledge of zones and the DNS providers, it is not manageable, but it is easy to introduce some errors. And there are some tools to manage DNS records across multiple DNS providers. For example, there is AutoDNS, it is infrastructure as code, and it provides a set of tools to do DNS record management across DNS providers. And Netflix has a denominator, which is a Java library that does the same thing. And it also has a command line too to make things easier. But these two things require the end users to have the knowledge of the mappings between the zone vendors and the zones and the DNS providers. And in previous talk, Sidan and Sile has talked about ExternalDNS, which is another tool to manage DNS records across DNS providers, but it is mainly used for Kubernetes. So what we need here is a DNS provider agnostic REST API endpoint or microservice. Basically, it has all the details of the zones and providers, and it behaves as a single REST API endpoint in front of all the DNS providers and provide a single standard interface to all the end users. And it also provides the standard responses to the end users. And because it is a REST API microservice, it needs to be highly available and scalable. Another good thing to have is we want to make account management easier by using this system. So to solve the above problems and satisfy the requirements, our team has built a microservice named Athena, which is a DNS provider agnostic REST API endpoint. And we host this system on cloud platform. And we use this tool Athena to manage tens of millions of records in thousands of zones. And they are distributed in multiple DNS providers. And our customers are our own team, the DNS teams, many operational teams, as well as our application code and the various automation tools. So we have a lot of customers. And Sile handles over 1 million create, update, and delete requests per day. This system has been running in production for almost 4 years, and it is highly available and scalable. Here is a very high-level overview of Athena. So basically, we did not only build Athena itself, but we also built the entire ecosystem for Athena. For example, besides building the Athena primary side, we also built the disaster recovery side for Athena. So in that case, if something goes wrong, we can fail over to the secondary instance. To detect the possible problem of Athena, we also built a monitoring system, another microservice, and integrated this monitoring system with PagerDuty. So if something breaks, our team can be paged and go to the bridges to fix the problems. And we also saw the numbers on the dashboards. Another thing we built for Athena is analytics system. So basically, it can collect different usages of Athena. For example, the number of CRUD requests every single day, or and also some performance metrics, and we show this in different dashboards. So a key problem in the previous slides is how we can manage this zone vendor or zone provider mapping. So we built another separate microservice that pulls the list of all the zones from multiple DNS providers and pulls them into database. Besides this automation process, we also have a REST API endpoint that can be used by the admins to manually create the mappings between the DNS zone and the providers. And here is an example of how this looks like in our database. And here we can see for example.com, it is on provider A. So that means if a CINA receives any request in example.com, it will check database and see, okay, so this is the correct provider, and I'm going to use the REST API specifications for this provider, and then standardize or translate the responses from provider A to the standard response to the end user. And so another thing we want to mention here is CINA makes account management easier. So let's say we have 20 teams and 20 engineers on each team, and we have 10 providers. So in this case, if we do not have a CINA, we will have 4,000 accounts. It is a nightmare to manage all of these 4,000 accounts. But if we use a CINA, we only create a single account for each team on each provider. So that is 200 accounts. After that, we create account for every engineer. So that is 400 accounts. So in total, we only create 600 accounts, which is about 15% of the 4,000 accounts. A similar thing applied to the scenario when engineers leave the company. So it also makes the deletion of the accounts easier. So as a CINA is a REST API endpoint, there are multiple ways to talk to a CINA. The teams can write Java code, Python code, or whatever code to directly talk to a CINA. They can also use curl command, postman if they prefer some visible data to talk to a CINA. Our team also developed a command line tool that can be used by different teams. And here is an example of this command line tool to create a CNAME of foo.example.com that points to bar.example.com. With this tool, the teams can easily write script to manage hundreds or even thousands of DNS records. We do have some future work for CINA. First thing is we want to support atomic transaction. And a few examples we are thinking about is maybe multiple domains need to be created or deleted at the same time. So in this case, if one creation fails, then the entire transaction should fail. And another scenario is a zone can be hosted on two providers in active-active mode. So in this case, the DNS request needs to be successful or failed on both of them. And this is another example of atomic transaction. Another thing we plan to improve is to have some fine-grained access control, like type level access control and also record level access control. Besides these two directions, the third one we are looking at is more authentication methods, and we would like to try MTLS. In that case, we can do some authentication and authorization based on the naming convention in the MTLS. And I believe this is the end of the talk, and I'm open to questions. How is the process of verify and rollback by the DNS zone record changes in a CINA? Okay, so a CINA is more like an agent that talks to multiple DNS providers it does some basic verification of DNS records, like maybe checking the length of the DNS record. But I'm not quite sure about what this rollback byte DNS zone record changes mean. So basically, the end users maintain the logic, or they need to know what is the correct DNS changes they want to do, and then they just use the Sile as an agent to make the changes. The next question is from Patrick. The question is, how do you handle provider changes for existing zone? And if the zone uses something like record type not available supported on all providers. One example is proprietary implementations of CNAME at Apex. Yeah, that's a great question. Okay, so for the first question, how we handle the DNS changes. If we come back here, these slides, so we use two ways to do this. One is we have a microservice that pulls the zone list from all DNS providers, but we do have a way to manually override that. And then when we do the zone migration, the system admin will go to Sile and use the admin REST API endpoint to override the zone weather mapping for the migration. And the second part of the question is how we handle the features that are not supported on providers. So currently, Sile only supports the commonly or the not commonly used. I mean the types of records that are shared by most DNS providers, like CNAME or A record class A. So integrating the more advanced or different behaviors of these from different DNS providers is also on our roadmap. But for now, the Sile doesn't support those advanced features. I believe that's all the questions. Thank you so much.
Right, that's the end of our first session of the afternoon. We're going to have a break for about 30 minutes, and we will start back at 7:15 UTC PM or 3:15 Eastern Time. I would like to thank Comcast and Verizon for being sponsors of the workshop, and I see you in about 30 minutes. Welcome back everybody. So we're going to get started with session 4, which is actually 2 sessions. We're going to have 2 talks, have a small break, and then 2 other talks. I would like to thank our sponsors, Comcast and Verizon, and we're going to get started with the next speaker, which is going to be actually a video, but the speaker will be available to answer questions. So the next speaker is Petr Špaček from ISC. He's going to talk about performance effect of DNSSEC validation on a busy resolver.
Welcome to talk, which should have been called Demystifying DNSSEC Validation. My name is Petr Špaček, and I work with ISC on all things DNS. In this talk, we will have a look at the traditional wisdom that the DNSSEC validation requires more resources. As usual with wisdoms, it doesn't actually say what resources and how much you need for validating, and we don't even know whether it holds in 2022. So we will try to approach this with more scientific rigor. Of course, everything starts with the dataset. For benchmarking resolvers, it's absolutely crucial to have realistic data. Luckily, a friendly European telco provided us with the real traffic flowing to their resolvers, of course anonymized, and the traffic consists of a mix of landline and mobile clients, everything mixed together in a huge PCAP. For purposes of this talk, we want to test two ends of the spectrum. On one end, the not really loaded resolver with 9,000 queries per second, and the other end of spectrum, 135,000 queries per second, which is heavily loaded resolver. Of course, when we talk about the QPS, keep in mind that the queries are not equal in a sense that different queries require different amount of resources on the resolver side, most importantly depending on cache hit or cache miss, answer size, and so on and so on. For our purposes, we took a huge data set and downsampled the data to smaller sets of smaller QPS. To do that, we had to always keep the complete set of queries from a single client, so we were basically downsampling based on the source IP address. If the client address was included in the dataset, all the queries were included, and if it was not included, none of the queries were included. That's important, again, because we have to keep the cache hit miss rate exactly as it was. That's for the data. The test setup is not really surprising. We use a latest stable version of bind, 9.18.4, and always start with an empty cache, no surprises. We test two configurations of bind, one with validation enabled and second with validation disabled. That's the only change in configuration. Then the queries are simulated by software called DNS Shotgun. It's a tool which reads a PCAP and then keeps the exact timing of queries and replaces all the queries to the resolver. That was the simple part of setup. Then the hard part is obviously the internet. We need all the authoritative servers, including timing, latency, reliability, and so on, and that's super hard to measure and simulate. So what we do is that we actually measure against the live internet. Our test resolver is talking to the internet, and of course that causes lots of noise. To counter that, we repeat every single measurement 10 times, then do the usual post-processing. And for this talk, we are concerned with resources spent on the resolver side. So we need tools to monitor the resource consumption. To do that, we wrote a little scripts which basically scrape files in /proc and /sys, and then store these files on disk, including timestamps, and then later, after the test ends, we post-process the raw files in a form which allows us to draw charts out of it. That's for the test setup, and now we can have a look at the first scenario with 9,000 queries per second. Before we dive in, let me warn you. When I say 9,000 queries per second, it's not a flat 9,000 number which you would get from DNSPerf or a similar tool. You can see here that this is the packet rate from the PCAP we are using as an input for DNS Shotgun. And here the traffic jumps like crazy, and that's exactly what happens in the normal live network. So it's definitely not the lab setup. And here we can even see that around the second 500, something went wrong with a very small subset of clients which started querying like crazy and produced lots of queries which ended up being refused because it was complete garbage. But that's what happens in the real network, so that's what we have to take into account. Of course, this is talk about DNS, so we are obliged to be basically obsessed with latency. First, the traditional wisdom about DNSSEC validation would say, Of course, it will significantly increase latency because validation is complex and blah, blah, blah. Here we can see the logarithmic percentile histogram, and in fact, there are no big differences. First, let me describe the chart. On the y-axis, we have the response time in milliseconds. On the x-axis, we have the percentiles for the slowest queries. Let me give you an example. If you look at this point where the x value 10 intersects with y value 1 millisecond, it practically means that 90% of queries were answered within one millisecond, and 10% of queries were answered in 1 millisecond or more. For our purposes, we basically want to have the line on the chart as close as possible to bottom left corner, because that's where the smallest latency is. But in the end, it's not so important, because if you look closely, you can see that the lines, the blue line for validating configuration and orange line for non-validating configuration, are overlapping so much that it practically doesn't make a difference. The color background denotes the range of values over 10 measurements. So it's the latency difference between fastest and slowest of 10 measurements. As I mentioned, it's practically the same, and that's true even though we are focusing on the first minute of the measurement. So in the first minute, when the cache is completely empty, there is practically no difference between validating and non-validating resolver. If we fast forward to the very end, we can see a latency histogram for the last minute. So we were measuring for 10 minutes. Now the resolver was for 9 minutes working as usual, and then we took the latency for the last minute. Here the lines are even closer, the color background is even smaller, so the variation is smaller, and there is basically nothing to see. For 9,000 queries per second, the validation doesn't cause any difference. Okay, then next thing, the traditional wisdom says that surely we will need more TCP, because of course packets are bigger and so on. To measure that, we were focusing on a number of TCP sockets in use as reported by the operating system. Here there is practically no difference even at the beginning. If we focus on the last minute and average the values for the last minute, the number of sockets is exactly the same. Of course, the sockets in use at any given moment might not actually reflect the number of sockets over the whole period of time, because the socket might be so short-lived that our data sampling might not notice. So to account for that, we were measuring also number of TCP sockets in a so-called time-wait state. So practically that's more or less the sockets which were closed by the resolver once that DNS transaction was finished, and then the socket for a short period of time lingers in so-called time-wait state. This is also measured on the operating system level, and we can see that there is some difference, but it's like 14 sockets on average, and that's on a resolver which handles 9,000 queries per second, so that's actually irrelevant, the difference. For UDP sockets, it's the same story, nothing to see here. The traditional wisdom also says that surely getting all the DNS keys and the other DNSSEC metadata will cause more packets being sent out. And here, if we look closely at the chart, there is not really a difference. I mean, in the first second, there might be a visible spike or might not. And if we look at the average for the last minute, there is no difference whatsoever. Okay, so number of packets didn't increase, so surely the bandwidth must increase because they are the RR6, right? Again, not really. If you look at the chart, in the first second there is a little spike, but again, in the last minute, there is no practical difference, nothing to see here. The traditional wisdom also says that the DNSSEC validation is CPU intensive and surely it will burn your CPU, but that's not really true. Here we can see actual increase in the first minute or two or maybe three, or maybe not even that. But that very quickly converges to the values for the non-validating configuration, and again we can see that in the last minute there is practically no difference. I mean, it's on average 2% difference, and here 100% means one CPU core. So 2% on one CPU core means practically nothing. And then last but not least, finally we found a chart where the validation makes a meaningful difference. This is the memory usage for the bind resolver, and here we can see that there is difference which is reproducible and actually not within the measurement error. That's a new thing here. And if we focus on the last minute, we can conclude that the difference is approximately 10% increase for the validating configuration compared to non-validating configuration. So that's finally something where we can conclude that yes, the validation does make a difference from the resource consumption perspective. That was for the simple case with 9,000 queries per second, so like not really heavily loaded resolver. Let's have a look at the other scenario at the other end of the spectrum with heavily loaded resolver handling 135,000 queries per second. Again, we start with latency histogram. Here, we focus on the very first minute with completely empty cache. And we can see that in this case, the validation does make a difference, and it increases the percentage of responses which didn't arrive within client timeout. Here, the client timeout is actually 2 seconds because that's the value typically used by Windows clients. On the other hand, we can also see that even the non-validating case has a problem because the resolver is not warmed up, the cache is empty, and more than 2% of queries for the non-validating case are not being answered in time. So the validation itself is not a problem, the resolver is just not keeping up. Let's focus on the latency for a longer, in more detail. Here we have the same histogram for a second minute. So now the resolver was running for 1 minute and was filling its cache and answering as usual. And now we are plotting response time for the second minute. Here we can see that the resolver is keeping up. That's good. And there is some measurable difference between the validating and non-validating case. It's slightly worse for the validating. So we can go on and go on minute by minute. In the third minute, the lines are even closer. And now I will create an animation for you and cycle through the other minutes. And you can see that it is converging. And in the last minute of our measurement, in the 10th minute, we can see that again, the latency histogram lines are so close that it's hard to say whether there is meaningful difference or not. If we were really reading the tea leaves here, we could conclude that if there is any difference, which it is approximately 1 millisecond penalty for approximately 1 or 2% of queries, and that's about it. So that's the impact of DNSSEC validation on latency for a really busy resolver, which is handling 135,000 queries per second. Okay, so what about TCP? Does it make any difference if we have lots of queries going on and the validation enabled? And it turns out that there is little difference. There's like 5 sockets on average in 5 more TCP sockets in use on average on a resolver which again handles 135,000 queries. So 5 sockets is nothing. If you look at TCP sockets in time wait state, we can see that actually there is some difference. It's like 200 something sockets, but again this difference will not require you to change the operating system configuration to, you know, enable more open file descriptors at the same time or anything like that. It just works. For UDP sockets, again, no surprises, the difference is really small. For packets sent out, finally we can see some difference, but again, the resolver is handling more than 100,000 queries per second, and the difference is like 50 packets per second more going out, so nothing even notice. For the bytes coming back to the resolver, the difference is actually not measurable. It's not significant in any sense. CPU time. Surely the traditional wisdom suggests that now the CPU must be burning, but that's not the case. If you look at the comparison here in the first couple minutes, there is some difference which we can see with naked eye on the chart, but it very quickly converges, and again the validating and non-validating configurations are pretty close, and in the 10th minute the difference is like 22% increase of CPU time consumption, and again let me remind you, 100% is 1 CPU core, so basically DNSSEC validation for this many client queries requires quarter of 1 CPU core, and that's about it. So really not anything you would notice in practice. And for memory, again, that's the only significant chart. Here we can see that the increase is approximately 9%, and that's computed over the average values over the last minute. So that kind of confirms that, of course, it requires more memory to store the data, but that's not like super significant here. And that's about it. We can conclude from our measurements that the DNSSEC validation has negligible impact on latency, bandwidth, CPU time consumption, number of operating system sockets, or basically anything else except memory. The memory increase is roughly 10% increase for the validating configuration, but that's the only cost which we actually found might be significant in any deployment. If you have any questions about the measurements, tooling we use, or anything else, at any time you can contact the bind users mailing list. Of course, you can email me directly. Email is on the first slide. And that's all from me. Thank you for your time.
Okay, perfect. So quickly to the questions. What fraction of the sample queries were in signed zone? And also fraction of DNSSEC signed names. I will answer these questions together because the answer is I don't know. It was 81 million queries in 10 minutes, and I didn't go through all of them. And estimating that from the statistics is not exactly easy because number of validations is not the same as number of queries because it depends on error sets and so on and so on. I don't know. Did non-validating case set DO equals 1? The answer is it depends on what the client did because we were replaying the PCAPs. So whatever the original client sent, we were replaying that to the exactly the same, just the configuration in the resolver was different. So whatever bind does is what we measured, and that means that we were measuring actually the impact of the configuration knob, not the theoretical case, but we were measuring what happens if you flip off the switch from DNSSEC validation off to on or vice versa. So next question. It would be also great to have some instrumentation on a typical client, topological position, latency, etc., with the validation, non-validation on the responses from the same resolver. Well, that's not actually a question. It would be great, but that's super hard to do. I've spent a couple of years doing these kind of measurements, and it's super hard. If you do that, please tell me how. Puneet asks, what % of queries are... okay, that's the same question. I can't answer with straight face. Sure, the last question. How much time elapsed between the sampling of the traffic data and running of the experiments? How would a large delay with an expected volume of change to the external internal delegations and signing, etc., impact the results? That's excellent question. The data set was taken February this year, so it's approximately half a year old. And it very much depends on the data set. It can be complete rubbish 2 weeks afterwards when, you know, the huge bunch of zones is migrated to another provider and DNSSEC enabled or disabled, or it can be the same. There's no way to tell. It's just, you know, one data set, one snapshot in time. You cannot really say without simulating the rest of the internet and changing only one piece of it, which is something I really don't have tooling to do. And that seems that it is it. Any other questions, quickly?
Thank you, everyone.
It doesn't seem like it, so thank you for your attention.
And now let's move on with Paul Hoffman from ICANN. He's going to talk about round-trip times between resolvers and the root server.
So thank you. Hi, I'm Paul Hoffman, and I'm going to talk. This is a lightning talk, so I will talk even faster than I normally do on some measurements we did on round-trip times between specifically resolvers and a root server. And as you can imagine, the a root server is the one from ICANN. So quick overview of the short presentation. We know that resolver operators ask root server operators, you know, they want better round trip time. So we'll cover that a little bit. I think it's useful to answer them with comparisons to the real world, cover that. Then I'll talk, the meat of the presentation is how we did an estimation with the IMRS, which is the LRoot data. And that's sort of, I hope, the interesting part of the talk is we did it in a bad fashion simply because that was our restriction. And then I have a request at the end for the other root server operators in the room. So, you know, root server operators get asked, oh, hey, can you put an instance near me? You know, I want better round trip times and such like that. And those can fall into two sort of general categories. One is that an operator who says, well, I want to get at least average. You know, I don't expect you to do great for me, but I want to have at least average. So we need to know a median time for those. And some resolver operators say, oh, I think we have terrible. I think we're like the worst. And so it'd be nice to be able to tell them, well, here's the round trip time for like 90%. And I did some research and I didn't find any root server operators who had published this information. So I said, okay, great. We have the data, let's look at it. So estimating the round trip time became a little bit funny because the thing you would normally do is get a sample of all the queries going to your root server instance, send them queries or pings or whatever, and just measure the round trip times. And in fact, that's what I'm asking the rest of the root server operators in the room to do. We can't do that at ICANN because our agreement, which is very public, you know, we have the agreement with the instance holders, says that no other data is available or is collected by ICANN. So we can't actually like send queries for timing from our instances. But of course, hey, we're engineers here. That doesn't stop us from estimating. So what we did was, since we have all of the traffic, and normally most people think of this as query traffic, but query traffic comes with some IP headers in it. And the IP headers has the IP TTL value, which is hops. I want to be really clear here. What you get in the IP header is the number of hops between the querier and you. And so what I wanted to see was, could we sort of convert that hop count into round trip time? So how would I do that? So I started off with just a full day's worth of data from it, looking at, again, at the IP TTLs, and then you'll see in a couple slides what I did with that. So there was about, for that day, which was recently, about 1.7 million obscured addresses, and that's obscured by, for IPv4 at /24, for IPv6 at the /48. So that seemed like a pretty good data set. And when I took all of those together across all of our instances, and some of our instances are in obscure places with not very good connectivity to them, some of them are in data centers, the median IP TTL, and again, this is hop count, is about 10.5 hops for a query coming in. And then the 90th percentile is about 18 hops. So that's sort of interesting that the 90th percentile is about twice as many hops as the median. And just as a caveat here for anyone, not only who runs root server operators, anyone who runs any old router at all, you know that reverse path and input path are not always the same. So this is really just rough estimation. This is just a guess that we were doing. Now, to get the correlation between the IP round trip time and an actual milliseconds, I used RIPE Atlas. We did the 10,000 probes, and we did from the 10,000 probes to the IP address of LRoot. So this is not exactly what you would get going from all of the resolvers, but what we're doing here is not trying to get round trip times in general. We're trying to get a measurement of round trip time in hops to round trip time in milliseconds. And so from the RIPE Atlas data, the 10.5 hops, which was the median, comes out to be about 33 milliseconds, or we can call it 30. And then the 90th percentile of 18 hops is about 60 milliseconds. So again, this is much rougher than somebody who was able to do a direct measurement, but we thought that was okay. And again, the RIPE Atlas probes aren't in all the same places, but looking at the lines, I would say it's probably a reasonable estimate of round trip time to hops. And the other thing I would note is around the 90th percentile in the RIPE Atlas data, at about 18 milliseconds, I'm sorry, at about 18 hops, it got a lot worse. It got very, very janky. But these were our good guesses. So before I go to the request, then there's this question of, well, if the resolver operators are asking, well, I want to get closer to a root service system so that I get better service. Is this good? Is somebody who's only at the 90th percentile, in the last 10%, is that bad? We never hear people, even at the 95th or 99th percentile, saying, there is an effect on my users, I need something better. So I am not trying to answer, is this good? We could have long debates about it. There are no numbers showing that, but I want to be able to answer to people, how are you doing? Faster is always better, but if it's better by an imperceptible amount, who cares? It's sort of the same kind of thing if you go to a salad bar with unlimited, you can fill up your plate. And if you take one piece of lettuce off of your plate before you go back to your table, that's not as good. You're not getting as much lettuce, but you're not going to notice the difference. So here's my last slide. It's a request to the other RSOs in the room. You all can probably do this measurement better than we did. That is, you can probably do the sampling and then go out, and send a query. It either can be a DNS query where you get an NX domain or refused, and or it could even be a, just a ping or whatever. If you all could do that, I'm happy to put it all together. We can see if these sort of like derived numbers that we did are the same as yours, publish it and such like that. I think it would be useful. We can certainly hand it off to RSAC or whatever. So that's it from me, and I am happy to take questions.
All right, thanks, Paul. So yeah, there is a few questions. The first one from Habi, which is, do you get enough TCP traffic that you could get nice latency data from the delay between packets in the TCP stream?
We didn't differentiate between TCP and UDP just because we don't have, in the data set I had, we didn't have it. But again, we're not getting timing anyway, so it wouldn't help us at all. It certainly would help the other RSOs who might be doing this measurement.
Thanks. And then Brian Dixon, what about RTT from TCP traffic fraction and maybe setting TC equal 1 to force some extra data sample?
That would very much hurt the traffic we're getting. These are supposed to be silent measurements. I think this is true for all the root server operators. Measuring is much less important than serving. So serve as best as you can and do whatever measurements you can after that.
And another question from Brian. If this is a root server serving TLD info, how much is garbage? And maybe track resolvers to see if specific resolvers are apparently doing aggressive NSEC to block garbage. And wouldn't that help end clients, and wouldn't that help the end clients a lot more?
Okay, all of it's possible, completely irrelevant to this presentation where we were really just looking at how long does it take, and when someone says, I want better service, do they actually? But yeah, there's plenty of data on that. In fact, if you go to the LRoot website, we have up-to-date charts on that all the time.
All right, thank you. There is no other questions. Thanks a lot.
Great, thank you.
We're now going to have a small break, and we are going to be back at 20:05 UTC or 16:05 Eastern Time. Welcome back, everybody. So we're going to get started with our last sessions of the day. We have two presentations. The first one is going to be Duane Wessels from VeriSign talking about ZONEMD and the root zone.
So hello everyone, my name is Duane Wessels, and the title of my presentation is Message Digests for DNS Zones, including a little bit about plans for the root zone. So I should apologize in advance if some of you have heard this before, because this talk or a very similar talk has been given in a number of forums with the goal of making people aware of what's going on. I might sort of skim over some of the early stuff, but basically, if you don't know, a DNS zone digest is a cryptographic digest over the data in a DNS zone. It's embedded into the zone itself, so it rides along with it. There's a new record type called ZONEMD, and sort of I use ZONEMD interchangeably to refer both to the record type and to the protocol. So the digest is computed by folks who publish zones, and then it can be verified by folks who receive or consume zone data. So it's all very analogous to the kind of thing that you're probably familiar with if you've downloaded software on the internet. You've seen a directory that has like a checksum file and then maybe a PGP signature over that checksum file or something like that. So this is the same idea, but it's done a little bit differently because we can embed the record directly into the zone itself. So this is all specified in RFC 8976. I don't think the co-authors with me are in the room. Wes and Warren were co-authors on this. So thanks to them for helping out with that. So the way this works is all the data in the zone is given as input to a digest function that has to be in a well-defined ordering and format. And you have to exclude, of course, the ZONEMD record itself. Otherwise, you have sort of a looping problem. And then at the end, you put the calculated digest into the zone. And ideally, everything is signed with DNSSEC for that extra verification. And there's a little graphic at the bottom that sort of shows the flow and how this works. So ZONEMD is designed to protect data at rest versus data in transit. It's useful when you're distributing zone data between primary and secondary name servers, especially in very complex modern environments, including sort of the root zone. There's been, of course, increased interest recently in serving root zone data locally, hyperlocal root or RFC 8806. And there are some other possible uses for ZONEMD, such as CZDS and RPZ, and your use here as well. So a few slides about how it looks. This is an example ZONEMD record, and the highlighted field is the first field of the record, which is the serial. So it has a serial field which has to match the SOA serial. Then there's a scheme field. Currently, there's only one scheme defined, which is called the simple scheme. And then there's also some private use code points reserved. After the scheme field, there's a hash algorithm field or a digest type field. The RFC defines SHA-384 and SHA-512, and then, of course, also some more private use codes. The big blob is the digest itself, of course. For SHA-384, this will be 48 octets. For SHA-512, it would be 64 octets. For private use, it could be something else, but the RFC says must not be less than 12 octets in the digest field. So this table documents the implementations that I'm aware of, the implementations of ZONEMD. The first one, which is named LDNS Zone Digest. Sorry, I sort of took over the name LDNS there, but this was the reference implementation for those of us that worked on the RFC. Unbound implements this as a version 113.2. There's an off-zone stanza which you can use to turn this on. The LDNS library includes LDNS sign zone and LDNS verify zone that also implement the protocol. Folks from Nick Chile Labs have a package called DNS tools implemented in Go that implements this. And by the way, the .cl zone, I believe, is maybe one of the first zones that actually are using this. They're publishing a ZONEMD record. If you try to query for it, you have to be a little bit careful because I think their record is not signed, so you might get a server failure if you're doing validation, but the record is there. NSD implements it. Power DNS, not DNS, not resolver, I believe, still work in progress. I think last I looked there was some pull requests or something. Bind 9, similarly, there is some work in progress. There are branches, I think, where you can go and see the progress. And then Perl's NetDNS library can parse the record only. A little bit more details about which versions of which implementations support this. I won't necessarily read all of these, but if you're interested, you can see which particular versions of these implementations, Unbound, NSD, NOT, and PowerDNS, are able to load a zone, including the record in its native format, and are able to verify the zone based on the resource record. I just learned recently that NSD 460 supports this, but you have to use like an external validation program. So it's not implemented sort of natively, but you can use LDNS verify zone to do that. This table shows which implementations, how they behave with respect to zone transfers of a zone that has the record. So at this point, the testing is sort of incomplete. I've been able to test Unbound and not DNS, NSD and PowerDNS. That's still work in progress on my part to fully test these. One of the things I'm interested in, though, is what happens if a name server is serving the zone and everything's fine, and then it's presented with an updated zone where the verification fails. So in the case of Unbound, the current version, you'll get a serve fail, and I've talked to the NLNet guys about this, and they're aware, and I think that's probably something that they'll look at. Not DNS is very good, and it serves the previous zone, so it ignores the update and will continue to serve the previous zone. This is an example of what it looks like if you enable this with Unbound, and you'd use the off the zone stanza, and you say ZONEMD check yes, and then you turn on debugging, and towards the end of the debugging you'll see some lines that say, yeah, I checked the ZONEMD record and it was found to be valid. This slide you've probably seen before if you've heard this talk. This is just here to sort of maybe convince people that the CPU requirements aren't really all that horrible. This test was done a few years ago on almost all of the TLDs. The COM zone was actually too large to load on the system that I had access to, but highlighted are the net zone, which was the largest one that could be tested, and then the root zone. So to calculate the digest for the root zone is about 100 milliseconds of CPU time. All right, so a little bit more details about what the plans are for adding ZoneMD to the root zone. There's an ICANN group, RZERC, which is the Root Zone Evolution Review Committee, and they've made recommendations for adding this to the root zone. There's these 4 recommendations listed here that say things like, we need to make sure that that everyone's prepared for this, that the root server operators are ready and nothing's going to break. Make the community aware of the plans. I believe ICANN will be probably announcing something shortly about some communications that they plan to do around this as well. There's a recommendation around working with name server operators, implementers to encourage them to implement this, and that ICANN and VeriSign should jointly develop a plan for deploying this to the root zone, and that's still work in progress as well. But at this point, what we're sort of thinking is that the record would be added in 2 phases. In the first phase, there would be a private use algorithm for the ZoneMD record, and then in the second phase, it would be the SHA-384 algorithm. One open question still is the presentation format that would be used in versions of the root zone that are published that way, such as on the Internet servers, and the next slide we'll talk about that in more detail. And then lastly, we're sort of expecting, or not expecting anymore, but one of the things that needs to happen is the root server operators are coming out with a joint statement confirming their readiness to accept the ZoneMD record, and basically stating that there will be a 1-year period during which they will not enable the verification. They will always serve whatever they're given, even if, for example, the ZoneMD record didn't verify correctly. So to the question of what the record should look like in its presentation format, the examples at the top of the slide, these are equivalent records. One is using the native format and one is using the generic or unknown RR type format. For distributing the root zone within the root server system, this doesn't matter at all because that doesn't happen in the presentation format. It happens in wire format. But it could matter in situations where the zone is published as a text file, such as on internic.net servers. The thinking currently is that the generic format is probably minimizes potential disruption from folks that do their own sort of parsing or using older tools. This is we're probably in precedent-setting territory here, and this will be something that's very difficult to change. And there are also concerns that if we didn't go with the native format this time, then when some other record type needs to be added to the root zone or some other critical zone in the future, there might be some temptation to continue using the generic format approach and not using the native approach. So this is something that's still a little bit up in the air. If you have thoughts about this, would love to hear them either today or privately. I believe that's it. Thanks.
Thanks, Duane. We have a question from Abby, which is no DURZ period, deliberately invalidatable.
Okay, so talking about the DURZ, the deliberately unvalidatable root zone technique. So that's essentially what we're trying to accomplish with the first phase of this, which was using a private use algorithm. That phase is expected to last for only about 2 months, however. So there will be a period in which there would be a record published in the zone, which no one should be able to verify because it's a private use algorithm.
Hi, Ed Lewis. Okay, so I had 2 responses to your last 2 slides. Do you want to go back? The one before that, about not verifying it. One before that, you talked about not validating I would suggest validating it, but then not reacting to the result. I think that would be I'd rather see that saying, yeah, it's validated, because if you find it's not validating, you're not discarding it anyway. I mean, it's not affecting it, but at least we know that there's something not right with the validation of that. So on the last slide, you asked about the format, because I have something which captures ZONEMD records that are out there today. It was a TLD that's been publishing it for quite a while. And my sub dumps it out as the generic format because I didn't even know, I haven't gone back to add that to the code to parse it. But I would encourage using the first format as soon as you can, because I think in this use case, probably the result is not going to be operational. It's going to be for research or for other purposes. And there's more tolerance for things not working in that arena, because then you go back. Like for all the stuff I have, I've logged all of those messages. I can go back now and throw them into the hopper and then parse them, and they're, for what I do, it's good. I think so. I think you'd want to see it in live format as quickly as you can. I think it would just be better that way. Keeping the generic format doesn't really help here because it's not operational.
All right,
I think.
Thanks, Ed.
Then there is a question from Petr Špaček. What happened for IXFR? Is the ZONEMD transmitted to or computed by receiver? Same question for dynamic updates on a zone having the records already.
Okay, so if you are using a zone, or if you're using a system that uses IXFR, and you are publishing a ZONEMD record, then essentially your software, your system needs to recompute the zone digest for every update. So every IXFR would include the ZONEMD record. I haven't tested that case. I don't know if that's a supported feature or ability of the software at this point, but that's what would need to happen with ZONEMD as currently specified. And similarly for dynamic DNS updates, it's the same thing. If you did read the RFC, you would see that ZONEMD is not recommended for use in zones that are very large or that have a high rate of updates. So there is some future work to be done to accommodate those types of zones with the ZONEMD feature.
Thanks, Duane.
Okay, thank you.
Next, we're going to have a talk from Yoshiro YONEYA from JPRS. It's going to be, are we ready for NSEC 3 guidance?
Okay. So this is Yoshiro YONEYA from JPRS. Today, I'd like to talk about NSEC 3 guidance, which will be published as an RFC, BCP RFC very soon. So the background is, as I said, NSEC 3 guidance, which is a new BCP RFC published very soon. So the technical background is already talked by Victor Noktobi at ICANN 17 DNSSEC workshop, so please refer to the slides. So the NSEC 3 guidance affect both zone publishers and DNS validators, but the timing of when they will follow NSEC 3 guidance may differ. So that due to this timing difference, possibly name resolution failure of TLDs that cause large outage of internet is highly concerned. So that I would explain about the possibility of the large outage as TLDs and propose some mitigations. And today's talk, I mainly focused on full resolver operators. And this is not objecting to NSEC 3 guidance, but aiming to smooth deployment of new BCPs. Okay, the key point of NSEC 3 guidance is it premises that they indicate, the guidance indicates that using iteration count larger than 0 is less effective than expected and possible security threat. So that the new best practice for zone publisher is iteration count of NSEC 3 0 must be used. So see, this is NSEC 3 parameters. So SHA-1 is only one selection, and the flag is 0. It is also only one selection, and 0 for the no extra iterations and empty sort. And the recommendations for validation resolvers, such as public resolvers and ISP resolvers, the validating resolvers may return an insecure response for iteration larger than 0. And also, validating resolvers may also return a sub-fail response for iteration count larger than 0. The may means it is optional, and I believe that experienced resolver operators will employ the option prudently, but it is not sure. So the impact to TLDs using NSEC 3 is DNS name resolution of TLDs using NSEC 3 with iteration count larger than 0 may be resulted in insecure or sub-fail someday after the publication of the BCP RFC. And major DNS software or service provider developers are favorable to NSEC 3 guidance. Therefore, the default setting of DNSSEC validator will follow the BCP in the future. I'm not sure the correct timeline, but in the future, probably. And the impact to, I'm sorry, so, and especially when large public DNS resolver services or large ISPs using, who have lots of customers started to follow BCP. TLDs not following BCP will be possible to become unresolvable globally. And this is a fear for large outage. If this happened, customer support of ISPs will be overflowed by claims from the end users, and therefore the operators will put the outage TLDs in NTA permanently, negative trust anchor. ATM is for negative trust anchor. And this is a very negative practice for DNSSEC deployment. And the recovery from this practice is very hard because operators will not change their practice so often. And this is a list of how many TLDs will be affected. So I counted 1149 TLDs in total. So I'm sorry, there was an error around here. The owner is not the TLD. It is a column label. So please remove owner from here. But it is still more than 1,000. So there is a proposal for avoiding large outage. And at TLD side, the TLD change their NSX3 parameters to the recommended value as soon as possible. At least iteration count to 0 and empty sort. And completion of changes is desirable within a half year after the BCP-RFC publication. And proposal for the validator side, please think carefully whether employing the option I mentioned before, and prepare a certain graceful period before changing the treatment of name resolution for iteration count larger than 0 to insecure or subframe. And please prepare at least prepare a half year and graceful period after the BCP publication. And if willing to change to subfail, please take staged approach. Just change to insecure first, and after the certain period, change to subfail, if preferable. And this is why I made this talk in DNS-OARC. At DNS community side, let's have a global consensus regarding to a certain graceful period prior to validator size changes. And this is my proposal that how about deciding a global target date? And how about thinking about the DNS flag date target for the changes in the resolver? So I'd like to discuss and get feedback from you about this, my thinking. Thank you. Questions from Edris. Would the NSX3 guidance be a candidate for yet another DNS flag day? I think it is a good candidate for the next DNS flag day. And the next question from Victor. So nobody will enforce iteration equal to 0 before all TLDs are compliant. I think so, but I'm not sure when all TLDs are compliant. And to reduce the burden for resolver servers, some target days for cutting off, changing to resolver settings would be better for the community, because the NSX3 guidance is a BCP for the DNS operators, both authoritative side and the resolver side. So next question from Victor also. I think too early for a target date. Yes, and though I'm not sure when is the appropriate date for the target. But It is not this year, I think, but next year or next to the next year will be a target. So I'd like to discuss this thing in the DNS-OARC. So feedback, please.
So we are a bit ahead of time, and we may or may not have a quick lightning talk. Rolling drums. Yes. So Wes Hardaker, for computer scientist from USC, is going to talk to us about GLS at a rock experiment.
All right, surprise! The talk you didn't know was coming. I'll make this quick, and I'm going to run through some stuff really fast because this is technically longer than a 10-minute talk. But we recently embarked on doing some experiments with TLS.
Can you speak closer to the mic, maybe, or take the mask off? Yeah.
We recently did some experiments between Google and ISI's root server. Google has sort of been experimenting with DNS over TLS and wanting to see what deploying dot would take. And we had questions: what would it take to deploy at a root as well? And how could we enable it? What would the operational costs be? And is there a way to do it safely without impacting the rest of our service? So we decided to start a small experiment about a month ago, and these are the preliminary early results. There's much more to analyze and do. On Google's side, they were probing us at port 853, and they were limiting their traffic load to 40 to 50%. So they didn't send everything over TLS if TLS was available, and that's important because in some of those numbers you'll see not everything came in over TLS. Some came over UDP and TCP. On our side, we isolated one backend at our Singapore instance, and we installed bind 9.18.2, which is the most recent one that supports authoritative TLS. We configured our existing deployment with our existing configuration that we do run bind occasionally on some sites. We rotate around things, but we didn't tune bind any more than just basically taking the defaults, which is something that we'd want to work on in the future. And we routed all of Google's traffic to that one backend that we had totally isolated, and the only thing it was handling was Google traffic and nothing else. So for the first week in our experiment, we measured traffic without TLS enabled, like how much traffic was Google sending us, how much CPU was it using, how much bandwidth is it using, how many packets, things like that. And then in week 2, we enabled TLS and measured again to see what was the change. I talked about the isolation. I'm going to skip this due to time. So the results are interesting, and we did 3 measurements, basically. We measured the number of packets per second, we measured the bandwidth used, and we measured the CPU used, both for the week without TLS and the week with TLS. And the other thing we did is we took that week and then smoothed it and time shifted it by week and divided. So you end up with a graph that shows what's the multiplication factor for without TLS and with TLS. So you'll see those in a minute. They'll make more sense when you actually see them. So this is the packets per second comparison. The bottom line, if we start there, is the normal traffic. The packets per second was actually pretty much equivalent, and there are actually 2 lines there, but they're overlapping and you can't see them. Whereas the top 2 lines were what happens when you turn on TLS, where the top line, I think, was the number of bytes received. And yes, and the middle line is the number of bytes transmitted when TLS was enabled, and the bottom line is again without TLS at all. So if you take those and you divide them, then we can actually come up with a multiplication factor. How many more packets per second were actually received? So the top line is the number of packets received in the multiplier, and the bottom line is the number of packets we transmitted back to Google as a multiplier. So you can see that it's, if you actually, I took the week and actually averaged it, so it's about 2.12 packets received. And we did not, I will note, do any analysis to figure out how much retransmission was happening in a session. It may have been just one transmission, it may have been more. I have not studied that, neither has Googled. Whereas on the transmission side, it was 1.54 packets over regular. Again, I'll remind you, this is not all TLS. This is a mix of some regular traffic and 50%-ish TLS. If we look at the bandwidth, we see similar results. Note that root servers receive far less bandwidth than we transmit. So the top two lines are actually both transmit, where the very top line is the transmit for TLS. If you look at the multiplier, which is sort of easier to consume, we received about 1.9 times the bandwidth that we did if without TLS. And we transmitted about 1.6. I'll remind you that we transmit more, so DNSSEC records and things like that actually brings down the transmit multiplier because we're transmitting more data. For CPU usage, we wanted to compare that to how much more CPU was it going to eat. The multiplier graph kind of lines out pretty flat at 1.6. So again, with about a 50-50 split, we used about 1.6 times our CPU. And this is with just handling Google traffic, this backend was doing very little. The CPU usage was very, very small. So here's the final table that shows the complete results, all the things that you just saw on the graph and what are the multiplication factors. This, again, is a 50%-ish TLS simulation, a little bit less potentially. So it comes out somewhere to 1.5 to 2x cost for all of these. We didn't compare memory. We didn't compare a bunch of other things. We'd want to compare TCP sessions and things like that, open files and things like that. So our conclusion is it's operationally feasible. And because we were able to do isolation, we did it with addresses, but we can also isolate by port and some other ways of isolating. We believe that we could actually do this even safely without impacting the rest of the service, and we have the resources to pull that off. The interesting thing is what happens after we started thinking about this further. First off, what are we going to do in the future? We're still trying to decide ourselves. We are making no commitments. If we do anything, it'll be more experimentation. There's optimization that needs to be done. We didn't do any, as I mentioned. We need to compare other parameters, as I mentioned. And we need to compare the results with other studies. My colleague John Heidemann actually did, a full analysis with a paper with a student that did replayed traffic. This was live traffic, real traffic. And I haven't compared the two results to see if those multiplication factors are about the same. And then, deploy safely to more sites. This was a single site. And profit, right? Why would we do this in the first place? There's always a debate of, does the root service actually need TLS support? I'm not taking on that bet today. But the last two slides are even more interesting, and the last slide is actually very OARC-centric, but the middle slide is what happens with our SAG002 stats. Some things aren't affected with TLS, load time, zone size, and things like that. Others actually, the traffic volume and the unique sources, well, right now those are split with a prefix, TCP dash or UDP dash, for example. And should we add TLS? I mean, it actually questions, is it TCP or is this another, protocol? Do we need to modify our SAG002? And then, to do some stuff, it would require internal name server logging, traffic size, and R-code volume. It's encrypted, so you can't pull it out of a PCAP now. You actually have to pull it out of something else, which is really similar for DIDL. What would this mean for DIDL, right? If we had TLS turned on in root servers for DIDL, right now, all of DIDL collects stuff over PCAP, and you get the IP, the QName, and all the DNS-ICI details. With TLS on, you can't really get PCAPs. You have to do sort of in-server capture and logging to get the full DNS details. Both bind and not support DNS tap today, but it wouldn't come out in PCAP format. You'd have to, it doesn't match the existing OARC formats at all. And a lot of this comes back to, this is my question to you all, what would the community want? If we end up at TLS at like every authoritative server in the future, what does that mean for DIDL? What would we want? Would we want a separate format? Would we want to collect those other data? And so with that, I'll leave the final question to you instead of you questioning me. But with that, anybody have questions?
So for the sake of time, we're not going to take questions, but I'm sure they can get back to you over the workshop chat or here.
Talk to me in the hallway.
Thanks a lot. All right, that's a wrap for day one. On behalf of the program committee, I'd like to thank all the speakers for the time they spent in coming with presentations. For people on site, we have a lot of COVID tests available, and we highly recommend that you take one with you if you don't have any, and please test yourself before coming back tomorrow. And yet again, I would like to thank Comcast and VeriSign for their sponsorship, and we see you tomorrow.